actually run into. One of the challenges with crypto in general is it doesn't lend itself very well to the kind of standard developer workflow, right? So when you're trying to figure out something you haven't done before, you hop on Google, you start looking around, and you look at examples, and you start figuring out how that code works, and then a lot of times you kind of massage that until it works, right? The amount of time required to go down to first principles for every tiny little tool that we have to implement generally is cost prohibitive. The downside with crypto is that will almost guaranteed create really nasty stuff. So if you Google like how to encrypt data in Rails, literally everything on the front page of Google in the first set of results is all wrong, right? So one of the goals that we wanted to do was kind of focus on the things that you would run into on a day-to-day basis. And so it made doing the demos kind of hard. Because we want to do something that was kind of at least reasonable real world. And we wanted to do what you would actually do in production code as opposed to kind of implementing AES from first principles or something silly like that. So, so a lot of the demos you see here are in Flask. You shouldn't need a whole lot of Flask knowledge. There's also a little bit of SQL alchemy in there and some of those types of things. And we'll talk about a couple of crypto libraries that we use to implement these things. Hopefully there shouldn't be too much knowledge. Paul will be pulling up some documentation, stuff like that. It's all out on the web. You can grab all this stuff later. But if you have any questions about those things, feel free to ask. And a big thing for us is like we've certainly got enough content to take us through the entire 3 hours. There's no problem there. But if there's stuff that you guys want to talk about, that's interesting to us as well. So if you have particular problems that you're trying to solve and you kind of want to think through, those can sometimes be a little more exciting than kind of a canned demo that we put together to kind of walk people through how to do passwords for the 15th time or whatever it is. So, all right. So quick introduction. So my name's Jarret Raim. I'm the security practice area lead at Rackspace, so I own all of our customer-facing security offers. So everything that we do from a security perspective for customers kind of falls under me. And I guess I actually have to like hand you the mic now.
Pass off.
Yes.
Yes, and I'm Paul Kehrer, and I'm a principal engineer at Rackspace, and I spend my time writing crypto code actually these days.
Yeah, so I talk about doing things, and Paul actually does them. So it works out well for both of us. All right, so we talked a little bit about the tools. So everybody should have the USB keys. You can yank it off of there. Paul tossed the link to where you can download the OVA from Akamai in the Python or in the IRC channel, which is right here. So if you can hop in there, I'll try to be monitoring that as we're going through and doing stuff. A lot of times, if you have a question, somebody else in the room may also have the answer. So it usually makes things go a little faster. So you're not waiting on us the whole time. If you want to do it yourself, you'll need these basic things installed on your laptop and functioning, which is why we gave everybody the OVAs. Sometimes it can be a little weird because we'll be compiling some C code, some of those types of things. All of the demos that we're going to talk about today are sitting on GitHub today. You can yank them to do whatever you want with them. It's kind of available for everybody. We haven't tested this in VirtualBox. It'll work in Windows, but other than that, should work. Yeah. So the password for the OVA is PyCon 2015, and the user is just the Ubuntu user. So if you boot that up, it should default to that, and just PyCon 2015 should get you in.
And that's all lowercase, even though that font wouldn't apply otherwise.
Yes. My fanciness bites us in the ass again. All right. So most of the day we're going to spend, excuse me, actually doing a lot of demos and kind of digging through code. But to give you an outline of what we're going to talk about today, we're going to focus on 4 major areas. So the first is passwords on authentication. Hopefully most of you have seen password authentication systems at this point. Most of the time, most developers are at least reasonably experienced with them. But as it is the #1 thing that we will implement most of the time, we'll kind of go through how we might see that. And we'll go through it with a point of view of especially dealing with existing systems that may have problems. So almost a remediation effort rather than necessarily starting from scratch. We'll talk about the one that generates usually the most questions in every kind of training or consultative enterprise that I've ever done is around key management. And so getting your head around how to actually use crypto is not particularly difficult depending on what types of problems you're trying to solve. Key management tends to be the sticky wicket. So we'll talk a little bit about how to do that, especially if we want to get into some of the modern systems around how you do that when you're starting to do configuration management or even talking about Docker and some of the other things that are floating around these days. We can get into that as much as you want. We'll also talk about data at rest. And then finally, we'll talk about signing and verification, assuming that we have time to get to it. So we'll see how it goes from there. So, all right, so we'll jump into passwords first. So one of the challenges with passwords, right? Fundamentally, a password is an encryption key, right? I mean, it is the secret that you are providing to an algorithm to protect something, right? The downside to passwords is that they really don't have the entropy that you need to actually be encryption keys, right? We all know this, right? They're relatively easy to guess. People choose crappy passwords. They reuse passwords, all of those things that matter a lot, right? And so when we talk about passwords, it fundamentally boils down to talking about key derivation, right? And in this case, what we're talking about is that we want these encryption keys to be hard to guess. We want them to be able to withstand brute forcing. We want them to be able to be fed into whatever encryption algorithm that we feel the need to use, right? And you can't do that with a raw password, right? So key derivation functions fundamentally take in these kind of low entropy secrets and turn them into high entropy secrets, right? And that allows us to use them in various different ways. So the four that you typically hear about, as you see, key derivation functions are PBKDF2, bcrypt, which everybody should be hopefully relatively familiar with, scrypt, and then HKDF, which we'll talk about as well. So when we look at a key derivation function, right? So fundamentally what it does is it derives one or more secret values, right, from an existing secret value, right? And this can be useful in a couple of different places. One is kind of the key strengthening point of view. If you're starting with something that's not very entropic and you need a lot more entropy, you need it to be a much stronger thing to be able to pass into an encryption function, you can use a key derivation function to make it stronger, take that weak value and make it stronger. The second piece of that is when you need to stretch it, right? So there are several different cryptographic constructs that require that you pass in multiple keys, but asking users to come up with multiple passwords or use them in various different ways is generally not desirable. And so a lot of times you can take an existing secret, stretch it, right, add entropy to that secret so that you can split it, for example, and use it as two keys for something like an encryption and a authentication key or something along those lines. Right. All right, so digging into kind of the pieces that we're talking about. So bcrypt is probably the one that most people have heard of at this point, especially if you were paying attention to the recent Slack breach. So it's based on existing cipher, which is nice, and it's true for both. Well, scrypt is a little more custom, but bcrypt especially is based on an existing cryptographic primitive. And the very nice thing about that is that we're able to go from what is a relatively new construct to it being trusted relatively quickly, right? And the reason we're able to do that is because the underlying substructure of bcrypt is very well studied, right? People have already spent an enormous amount of time looking at it. So how many people have heard of AES? Everybody's heard of AES? Yes? Okay, so back when NIST decides how to anoint certain algorithms as AES, and before AES it was DES, which is the defense encryption standard, right? They run these contests, right? We've been seeing a contest for SHA-3 that's been running for years now. So it's officially done. It's done. They haven't finalized it yet, but they picked one. And so a lot of times you'll hear people mention things like Blowfish or Twofish. Well, that was later, but these types of algorithms, right? And these were the names of the algorithms that were part of these contests before they were selected as a standard, right? And so in bcrypt's case, it chose to use one of those algorithms that was part of the competition, but was not chosen for AES, right? And that's what it uses underneath the covers to actually do its work, right? At this point, it's used as the default password store mechanism for a whole bunch of different systems, BSD being the kind of most prominent, but lots of other people are using it by default now. And you can kind of see a quick example here, although we'll dig into some of that a little bit later. It's relatively straightforward. I mean, I think what matters for bcrypt and scrypt, right, is the capability to actually make the password generation process harder, right? And in the key derivation functions, when we have this key strengthening and key stretching perspective, right, that's great, and we do need those types of things. Wow, that was loud. It like caught the microphone or something. What you want to be able to do is by making them strong, right, one of the things that we can do is make them harder to process, right? And this was bcrypt's kind of claim to fame, and this is one of the reasons why a lot of people use it, is it has what's called a tunable work factor. And most of these PBKDF2s have this, right? And the work factor basically says how much effort is your processor going to put in to generate the value, and it being tunable allows you to tune that based on what hardware you're running on, right? And so when we're generating a password, we want that to take as long as we can reasonably get away with, right? So when you're looking at your systems, one of the challenges that people kind of come and ask us about is, all right, well, what's a work factor and how do I decide what it should be? So the default for bcrypt is what, like 12, right? Yeah, 12 rounds. And so what it's basically doing is bcrypt is doing a whole bunch of calculation in the background. That's going to take a certain amount of CPU time to compute, right? Now, from an attacker's perspective, you want that number to be as big as humanly possible, right? But the bigger you make the number, the longer it's going to take your system to process and the more load on your systems, right? So how do you choose this number? Well, go ahead and run the algorithm in the way that you want to run it on the hardware that you're going to run it on your production hardware, right? And then tune it up as high as you can tune it, right? 12 these days is considered still a good default, right? I mean, it's fine. There's nothing wrong with that. If you can tune it a little higher, great, right? But if you're in a very latency sensitive application, you may not be able to tune it very higher. I wouldn't go under 12. You know, sometimes you see people go down. I think a minimum that most of them will take is 4, right? But anyway, you want to stay there. And so what that actually does is it means that it's going to take more compute time to calculate the value that you have in the end. So if an attacker gets a hold of your database, right, it will now take them exponentially more time to work through all of those passwords and guess them, because now it's going to take more time for them to compute. Because they're trying to do hundreds of millions of guesses, whereas you're only doing one when you're actually authenticating a user, right? So how many people saw that Slack got breached recently? This was pretty big news in the community, right? And for those of you, like, if you're in the security community, it was interesting. A lot of people who weren't in that community came to me and they're like, well, why does nobody seem to really care that much, right? And one, Slack did a really good job at incident response. That was great. But one of the things that they did is they were very, very specific about how they stored their passwords, right? And they were actually using bcrypt with a reasonable work factor. And so because of that, now you know how it works. You can look at that and say, okay, well, the odds of an attacker being able to really compute all of the passwords that's in that breach are relatively low. Right? The cost is going to be very high for them to do so, right? And so that's partially why the security community didn't freak out as much, because Stripe was doing the right thing in this case. That make sense? All right, so moving on to scrypt. Scrypt got very interesting. So we've seen a couple of things that matter when you're talking about processing passwords, right? One is you have the rise of nation states as enemies, right? So NSA, GCHQ, and these types of guys, right? And they have the ability to go and tape out physical hardware capable of running the hashing algorithm. And because of that, they can start to get into, what is it, the trillions of hashes per second that they can check on this type of hardware. We're also seeing a rise of that in the commercial world around Bitcoin, right? So now all of a sudden it starts to make sense to build hardware capable of calculating these hashes or these constructs at incredible rates, right? That screws up the work factor, right? So now all of a sudden, if you're running on general hardware, you have to tune a work factor to something that you can live with, right? But they're not running on general hardware. So even if you're using that work factor, it's in theory that these types of guys can compute hashes fast enough they can still start to break them. And so because of that, it was Colin that came up. Yeah, Colin Percival came up with scrypt. So the challenge at that point is not so much to make the compute harder, because the more if you make compute harder, adding hardware to the tape out that you're going to build is actually not particularly expensive or difficult to do, right? But you want to make that as painful as possible for the NSA or whoever's trying to break your stuff. And to do that, you have to make it as expensive as possible. That's basically the only option that you have, right? If they're willing to spend the amount of money to break your system, they will get it, right? The goal is to make it as expensive as possible. So what scrypt does is it adds another component. So instead of just processing, it adds memory hardness, right? Because it's much more expensive to throw memory on these taped out devices, right, that they're building to be able to crack this stuff, right? So scrypt is considered safe to use at this point. So it is more resource intensive on your backend. So you can choose to use that as well. The support for algorithm and language-wise is pretty good at this point. I don't think there's many major environments that wouldn't be able to use it. But you can use that. So the main difference between bcrypt and scrypt is that scrypt throws in this memory difficulty. I don't know if you wanted to.
It's one of the interesting counterintuitive concepts around password key derivation, that you want them to be slow, but at the same time you need the implementation that implements it to be as fast as you can make it. The reason is you don't want to trade that computational time you spent back to the attacker. So, like, for example, if you happen to implement bcrypt in pure Python and the attacker implements it in C, well, there's a strong probability that you're going to have orders of magnitude difference in performance unless you're using something like PyPy, perhaps. So this is why you end up with cryptographic constructs, for a variety of reasons, end up in C code mostly, with bindings into Python. That's both for performance and also for constant time side channel attack reasons. So like part of the reason why we gave you guys the OVAs is that we're installing 2 Python packages, both of which actually have compilation requirements. The bcrypt package uses C functions to be as fast as it can be. And the cryptography package itself actually leverages OpenSSL for almost everything. So that's why those things, those are not necessarily difficult to install, but they have significantly more dependencies than your standard pip install. Like a normal pure Python pip install, you're just going to pip install actually even passlib, which is a password library that we will be using in the first example. And when you pip install passlib, no C dependencies come in, so the whole thing installs very quickly. You don't have to worry about what platform you're on. You don't have to worry about having a compiler. You don't have to worry about having the right headers. You don't have to worry about the arcane magic that goes on underneath the hood inside setup tools and distutils. So those things are all unfortunate realities of cryptography in Python, and actually cryptography in any language that's not C.
All right, so moving on to the last two that we said we would talk about. So we have PBKDF2. So PBKDF2 has been around for a very long time at this point. So this is the only one that's really officially standardized, right? So it's got an RFC. It's part of the PKCS standards. So typically, if you're building a new system, you probably don't want PBKDF2, right? Bcrypt or scrypt is generally where you're going to want to go. The only time that you'll see this particular algorithm either required for an existing system or in a new system would be something that needs to fall under governmental regs, right? So that might be FIPS compliance or some of these other types of things. General recommendation is you don't want to use FIPS compliant code or FIPS compliant libraries anymore if you can possibly avoid it. But you still have a problem in that you may have to do that, right? But anyway, so you'll see those. And you can see kind of some of the, I don't know how readable that is at the back, but you can see some of the examples here where you're basically choosing what type of hash algorithm gets passed into it, a length, you pass in a salt, and then you tell it how many iterations. And that iterations in this case is the PBKDF2's work factor, right? And to be honest, you need to jack that up pretty high these days to get any kind of real protection, because it's using SHA-256, which is very, very fast. Although you can use other algorithms. And then finally, the last one that we hear about is HKDF. And we'll talk a little bit about this one, but this one you really don't want to use for passwords. It's really not appropriate for that particular use case. The only reason we include it here is because we do get a lot of people that ask us about it, or when you're Googling around, you may see it, right? You want to talk about your uses for HKDF?
Yeah, so the other three we talked about are explicitly password KDFs. Their job is to be slow. However, HKDF is much like a cryptographic hash, and cryptographic hashes are designed to be very fast. So HKDF's purpose is there's two different stages, as it says, extract and expand. Extract is an attempt to derive additional entropy for values of what entropy means. It's not really all that relevant in this case. And expand is basically creating additional keys from that single key material. So if you need to create round keys or other varieties of derivative keys, but you want those keys not to be reversible, then HKDF works very well for those purposes. If you see it ever used for passwords, it's just as bad as using just a single SHA. So that's a very, very big problem because it can be very quickly reversed. So HKDF is actually, so it's a relatively new construct. So actually in terms of like its use in protocols that you're familiar with, probably there isn't much in that. However, I'm trying to think. The actual PRF that is used in TLS has some, it's very strange. The TLS PRF predates a lot of formalized methodology, and so it's weird and actually does an MD5 and a SHA. Oh yes, my apologies. If I use acronyms that people don't understand, feel free to just yell. Yeah. So that pseudo-random function has some properties of the way HKDF works, but probably the best example, there's actually some stuff in OpenStack that does this now using derivative round keys. But yeah, I wish I could give you a better answer than that. So actually after this, we've got a little KDF demo, and actually I thought of a good way to do this, which is basically, we will go ahead and inside the OVA you've got a file, and actually I'm going to have to go ahead and hop this into this and make it much larger so everyone can read it. Are we getting big enough? There, that's big enough. Jarret, I think you get to be my mic stand.
That seems fair.
It's your role in life.
I enable people to do things.
All right, so what we're going to go ahead and do here is go into the PyCon 2015 crypto tutorial. So for those of you who have your OVA launched, or imported and launched, then what you can do is open a terminal and then CD into PyCon 2015 crypto tutorial. Inside that, you'll see all these files, or all these directories rather, and there's a crack demo. So if you go into crack demo, we can go ahead and look at you can look at the SHA-256 cracker.py. So it's a relatively simple app. what it's doing here is essentially it opens. It might help if you actually go to the right file. Sorry, my apologies. You actually want to go to generate SHA-256 hashes. All right, so in that file, you'll notice that it opens user shared dict words, which is a user dictionary that contains about 250,000 words on OS X and Linux. It then reads it in and splits it into an array, which is pretty much the most memory and efficient way to do it, but we don't really need to worry about that too much. Then it iterates 500 times, picking a random password, essentially a random single word from that list, and then it SHA-256s it. It actually does add a salt, as you can see here. It adds a salt of the iteration number, so you'll have 0 through 499 prefixed to the password. Then it hashes that and writes it to the file. So after 500, it writes 500 of those out, so we can go ahead and we can run that file, which if we run SHA-256 hashes. Then if you look inside the SHA-256 passwords file, you will see a whole lot of hexadecimal, specifically 500 lines of it. So once you have that, you can look at the SHA-256 cracker, which is a very, I want to emphasize this is a very naive password cracker. It does not attempt to be fast. All it attempts to be as readable as possible. So what it does is it opens that password file, makes a list out of it. Then it opens the dictionary file, makes a list out of that. And then for everything in the password file, it iterates over the entire word list, attempting to compute possible matches.
Which, based on the word list, would be checking against, what it is, 250,000?
So 250,000 different things, yes. It would check against 250,000 words. And of course, it has to try and figure out what that prefix is to the salt. So it's sitting there and it's brute forcing the salt as well. So this has roughly ON squared complexity, for those of you who like big O notation. That's not a good algorithm, and it's very slow at doing this. However, as we mentioned, SHA-256 is designed to be fast. So this is how long it takes to crack passwords. Every time you see a line, that means it has found another password that it has cracked using as many hashes as it needs to. So as you can see, a single SHA-256, even with a salt, is not a protection. And that's just with a single core on this laptop. You could easily scale this much more. For example, the SHA-256 hashes using Bitcoin miners can do 1.6 trillion per second. Now that's a little misleading in that if you have iterations, it's doing those all in parallel. It can't actually do them serially. So if you have one hash and then you need to hash it again, the Bitcoin miner does not give you perfectly linear speed up. But for example, you could do this with GPUs and a variety of other ways that give you easily into the billions a second. Whereas this laptop right now is probably doing somewhere on the order of about 300,000 per second with a single core. So the same thing actually exists over on the bcrypt cracker, which rather than go through the whole thing, we can just go ahead and generate the bcrypt hashes, which of course I should probably work on my actual. It also helps if I know how to spell. To actually run the bcrypt hash thing, you will need to work on tutorial, by the way. If you type work on all one word space tutorial, that will activate the virtual environment inside your OVA that actually has all this stuff installed. So once you do that, you can run generate bcrypt hashes, and then once it's generated those, you can crack the bcrypt hashes, or you can try is the more open statement. So as you can see, it's running, and we're not cracking anything. I've actually let this thing run for 30 minutes before and not seen a single password hash get cracked. I would expect it to run for a lot longer than that and still see nothing get cracked. To even confirm that this file worked, I actually had to set the work factor down to the minimum, and then I went and explicitly picked a word from the very top of the dictionary file, so that way I could minimize the complexity just to see it work. So I mean, this is a very easy and direct way of seeing that bcrypt offers several, not even several, many orders of magnitude improvement in terms of the amount of computational complexity the attacker must undergo if they happen to get access to your password database.
Yeah, and for almost any major framework at this point will include some support for bcrypt for you, right? So passlib does, if you install the bcrypt library, it picks it up. Django has support for it. I think it's the default now. Certainly we'll show Flask a little bit later. If you're in Rails, if you're in pretty much anywhere at this point will have reasonable support for bcrypt. So if you're starting a new application, you just need a way to store passwords, then generally the easiest way is to pick bcrypt and just kind of be done with it. If you want to use scrypt, no one's going to complain about it. It'll actually give you some additional extra protections. It's not as widely used in production at this point, and so it might be a little bit more of a, try it on something small first before you start to get there. But from a security perspective, it's perfectly fine to use something like that.
You mentioned the sort of obviously it takes more memory to use scrypt. Does that actually become a factor when you're choosing which do you like in production? If you have a huge user base, every time they log in, obviously you have a memory constraint down to the CPU.
Yeah, so the scrypt work factors are actually tunable on independent axes. So you can actually pick how memory hard and how CPU hard you want it to be independently. But yes, that's absolutely a statement. Like if you're memory constrained in your environment because you're Facebook and you need to have hundreds of thousands of sessions opening per second or whatever the system might be in that function, yes, you may have to seriously consider that. That said, I have never seen, and I mean, I work at a company with reasonable scale, not huge scale sometimes. We're not Google, but we work at a reasonable scale, and scrypt would still work fine in our environments. I would actually personally recommend scrypt over bcrypt, but bcrypt is perfectly fine. It's one of those ones where if you've chosen bcrypt, you have not made a mistake. Even if you've chosen PBKDF2, as long as your iteration count is high enough. And the way you turn that iteration count is just basically, as he said, you run it on your machine and see if that's acceptable to you. So like if you run a 500,000 iteration count and that makes your logins take 1 second longer, that's probably not acceptable. If you run it on a 100,000 iteration count and it takes 0.2 seconds, that probably is acceptable. And that gives you a significant amount of protection. Just for example, historically, about 5 years ago, Apple started talking a little bit more about what they do for their own logins. And so like their logins, because they need to be FIPS certified, et cetera, for a variety of government-y reasons, they use PBKDF2, and at the time they were using 10,000 iterations. So 10,000 at the time was fine. It probably should be higher now. I have not looked to see if they have actually increased it. If they have not, well, then they're starting to fall behind. That's one thing where scrypt and bcrypt can be more interesting. It's simpler to tune them than it is to tune PBKDF2.
And a couple of notes when you're looking at making this decision, right? We talked about putting it on your production hardware and running it through. I mean, at the end of the day, you're doing this on authentication, right? So generally when somebody's coming back, they've already authenticated and they're passing something and you're not doing it every single time. So you can kind of tune it based on that. The other thing to kind of keep in mind is tuning the work factor requires a re-encrypt of the password, right? So if you want to tune the work factor up at some point, there's actually a reasonable amount of work that goes into that process. Not as much as you might think, and we'll talk about that a little bit later, but there is some work there. So you really actually do kind of want to think about it before you launch it and run that stuff, because tuning it afterwards can be kind of painful depending on if you have a bunch of users that you have to deal with. Then you'll end up with Facebook's onion nonsense, right? But yeah, so either bcrypt or scrypt are probably the easiest ways to go. I think from a security perspective, we would both say, yeah, use scrypt, it's great. But you'll just have to make sure that it doesn't, knock over your auth server, or if you've got other things, if you're using auth and it's also doing something else and you're memory constrained, then you may have a problem. So.
All right, so it's actually time to go ahead and get going on an exercise. So for those of you who haven't yet, you should go ahead and copy that OVA and then import it using VirtualBox. Was that you, LVH? Was that a question? Oh, I thought that was you going tss. No. All right, so we'll walk around, make sure everybody's got that going. For those who want to get going going forward now, what we want to do is go ahead and get have the code, start the app up, and we'll walk through all this stuff up here. Take a look at how the authentication is being done, and then you're going to want to look at the database. We're going to modify that auth scheme and the code for that, using a KDF obviously for this, and then we're going to take a look at what happens after we relog in. And I will go ahead and I'm going to be putting a gist link inside of the IRC free node. And that gist link actually contains the step-by-step for anybody who wants to follow along in that fashion.
All right, was everybody able to get the OVA working? Everybody's got code up. Things are running. Yes, awesome.
Anybody who doesn't, don't hesitate to raise your
Yeah,
hand.
we won't make fun of you, I promise.
All right.
Can you remind us what the IRC link for?
Oh, sure. It's on Freenode?
Yep, Freenode, and it's Python-crypto is the PyCon-crypto. That's probably not going to help if I keep saying the wrong thing. Yep.
By any chance, do you have Ethernet?
Is the Wi-Fi dead?
My Wi-Fi just died, and I don't have virtual.
I don't think.
So on the
Yeah.
thumb drive, are you running, what are you running for an OS? Ubuntu. Ubuntu. That was the one thing, so I couldn't include VirtualBox installs for Linux because you need a different one for every distro, and I was like, oh, okay.
Yeah,
Yeah, we should be able to grab that.
I can do it.
If you want to do that, just grab the thumb drive and copy the dev file. Is there anybody else who is still attempting to get their environment up and running? So what is your problem? Or what do you need to do still? Sorry, that was the wrong phrasing.
So I've imported the OVA, and I'm just getting a ton of basically just D message. It's just throwing a ton of errors.
As it tries to boot?
Yeah, and it's slow. Eventually it does come up, but it's just slow. Like, you know.
It will be very slow.
It's probably not that slow. A bunch of
We're on like 10 minutes now.
yeah, not quite that slow.
Yeah. I've made all of my modifications in VirtualBox to accommodate different configurations that I have.
It would be wonderful if VirtualBox wasn't terrible software, wouldn't it? Do you have a functioning Python dev environment independent of this, or do you?
Yeah.
Okay. If so, then I would recommend you probably just go ahead and build that, and I can help you with that really quickly. Turn this off. And for those looking inside that directory, you'll see there are start and solutions. The solution is actually the completed code. So if you want to spoil yourself, you're certainly welcome to look at it. If you'd like to work along with us, then you're going to want to start in those start directories. All right, so now we can move forward. I'm going to need my microphone stand again.
I am the best microphone stand.
I don't know, you talk back too much.
It's true.
All right, so if we go one further forward.
One up.
My bad. So if we go through this now, and you walk through the app for a second, you'll see that it creates a Flask app. It grabs a database path, which it does just basically by introspecting the current directory it's in and then appending db.sqlite to the end, that's where it's going to write the SQLite database. That is, in this case, one passwords. So it'll just live inside this directory, which when things are this big, the wrap is not great. After that, it sets up the app configs. It sets a secret key of I am really secret, which we will talk about a little later. As you might imagine, this is maybe not the best approach to storing a secret key. It's also not the best secret key, but that's a separate issue. We then set up a SQL Alchemy object, and then we use a thing called a login manager, which is actually just from Flask. There's a Flask extension called login. We set up a class, which is a basic class for SQL Alchemy. It's got an ID, standard primary key. We've got a username, which we set unique equals true. That is actually mostly just to simplify what's going on here for now. So that way no one can have two the same username. And then we set a password, which is a string again. And then we set up the basic init. These are the typical way you would initialize an object in SQL Alchemy before you choose to commit it. All right. So you'll notice we have a few decorators on our routes. In this case, we say that / requires a login. We have a standard, there's a user loader, which is just another piece of the Flask extension stuff that we don't need to worry too much about. We have an app route for logout that logs out the user, and then we have this little login function that does some checks. And right now, you'll notice it filters by the username and password. So basically, if the username or password doesn't match, then when you ask for the first object of that query, you will get no DB user, which means you will get a failure. So if we attempt to run this, which we can do with a little Python app.py, of course, first I'm going to need to work on, in my case, I have a terrible name for it. Python app.py. We should see it's a running on 127.0.0.1:5000. And then if you go ahead and open up, I believe Firefox is living inside there. We'll go ahead and use Chrome for this. Go to 127 this. We'll see this nice little ultra secure site. The username and password for this is admin and password. As you might have, if you looked a little lower in the code here, what happens when it doesn't have a database is it goes ahead and just creates everything. So if we log in with our admin and password, we see this amazing logged in successfully and a logout with this amazing Bootstrap template I clearly spent huge amounts of time on. More than you'd actually think. I'm not a UI developer. So with that working, we've logged in. Now we want to go ahead and take a look at what's in that database. So if you ls your directory, you'll see there's a db.sqlite now. So if you run SQLite 3, and then pass db.sqlite as your argument, and then you type select star from user, you should see this. So that's user ID is 1, the login is admin, and the password is password. So as you might imagine, if this database ever got compromised, having the passwords be in plain text is clearly a terrible idea. I'm sure you all knew that before the 40 minutes we spent bloviating about it, but here you go. So we want to change that. We want to fix this. Like, how do you remediate this in an actual application that currently exists out there?
And while we're starting with the terrible option of a plain text password, this would be no different from walking into an application that was using MD5 or SHA-1 or SHA-256 or whatever, right? So if you're looking at, there's some slight differences and we'll talk about them when we get there, but fundamentally, like, when you're looking, especially when you're dealing with a lot of older software, these are the types of things that you'll run into, right? This is a pretty common piece where you want to go in and improve what's there today, right? And so we're going to go through one particular example, but one of the things that, how many people have heard of the Facebook onion? Anybody? Well, yeah, I know you have. So Facebook does a funny thing with their login. Over the years, they've made it stronger and stronger over time, right? And by doing that, every time you want to switch between one password to another, it basically requires a recrypt of that password, right? Or one password storage mechanism to another. So what Facebook did, instead of doing that, which is incredibly painful when you have 800 million users, right? They started to chain things together, right? And so you would see like when it's actually a whole bunch of code where it'll take something and MD5 it, and then it takes that and it SHA-1s it, and then it takes that and it runs it through bcrypt or whatever, and it does this over and over and over again, right? And so by the end, it's actually storing something that's relatively strong. In fact, it is strong, right? But it got there by kind of just stacking constructs on top of each other, right? And that's, I don't know, Facebook does it. Generally, it's a bad idea, right? It's not a very well-studied thing inside of the crypto community to pass the output of one hash function or one cryptographic process into another cryptographic process, right? And so when you start talking about a lot of the research that's been done on these things to prove that they are secure, or at least as much as we can prove that they are secure, when you do things like pass the output of an MD5 directly into a bcrypt, it's actually not really very well understood what that means to bcrypt, right? So you're extending yourself a little bit into space where you're not very well supported by the research and by the academics, right? And so that's why we'll take a different path that we'll walk through here in a sec. But there's a couple of different ways. And so it's very common to see this in applications where you have this problem of, okay, well, I need to take some older password scheme and make it better, right? PCI, for example, as you're getting PCI compliant, various other ways, there are things that kind of force you to do that. Your internal security people might come by and force you to do that as well. So you run into these things a lot. And so one way is to go that onion route, although we would not recommend it. This is the way that we'll kind of show today that makes a little more sense and still very easy.
It is probably worth noting that the Facebook onion has had significant. They have the resources to look into this, and one of the things they do is they drop HMACs in certain places so they can get their output into the right format for the next thing they want to feed into their weird onion function. And I can see LVH is. Yeah, I've looked at the onion pretty extensively. It isn't bad, but you probably don't want to pursue that unless you have 800 million plus users. At which point, do whatever. You guys are probably rolling on mountains of money. All right, so what we're actually going to do now is go ahead and remediate this. So the very first thing we're going to want to do is we're going to want to import some new stuff. So right here, we now want to have a from SQL alchemy _utils.types.password import password type. And for those who are interested, I should probably go ahead and paste the documentation for that into our. You close my gist.
I did.
Jerk. The documentation for that is here, which, there we are. So you're welcome to look at the documentation for what all this is capable of. We're going to use a subset of the functionality, but we're going to walk through a reasonable amount of it. So once you've got that password type, and thank you, whoever Nelson is, for pasting that in so people can copy and paste it. Thank you. Once you've got that going, the next step in our task is we're going to take a look at the user class. As you remember, our user class looked like this. This is what the password was. Password equals db column, db string 40, which of course just says it could be a 40-character string. What we're going to change it to is this, which is a substantially more complex object. So we're still saying it's a db column because that's SQL alchemy, but now we're creating a password type object. We're passing schemes, deprecated, and max length. So the schemes is the list of schemes that you want to accept. In this case, and that's an ordered list. So we're accepting bcrypt and plain text. So in this case, that means, of course, bcrypt is our primary and plain text is a secondary. Then we also pass a deprecated. And what deprecated means is that anything that's in the deprecated list will be migrated to the first option in the schemes list. So if it's already plain text, it will be migrated to bcrypt. If we had other things in here that weren't marked deprecated, for example, if we had something like SHA-256 crypt or something like that, that would not be migrated, but it would still be accepted.
When does the migration happen?
The migration happens when you put it in the deprecated list. At login. So in the case, this is where we get to the one little bit of a trivia around the fact that we're using plain text here. In the case of a pure plain text password, you have the password, and therefore you could go ahead and run it through bcrypt or whatever that one time to get what you need it to be in the future. In all other cases, say you have a SHA-256 already, unless you're going to go and crack your users' passwords, which you should never, ever do, you don't actually know the password until they log in. When they log in, they provide that password to you, at which point you can match it to the old one and then use the new hash function and then write that to the database.
Yeah, so how you go about doing this is somewhat based on why you're migrating and when, right? So if you have a reasonably strong, let's say you're using SHA-256, that's not good, right? But it's better than plain text. So maybe it's not an all-fire emergency that you migrated away, so you might be okay with people kind of logging in and migrating it over time. It's less painful on your systems, things can kind of, happen slowly over time rather than all at once. If you are breached and you need to migrate right now, right, then you may not do something like this, right? So one thing that you could do is you could set this up and then literally just go drop everybody's passwords out of the database. You no longer have them, right? And then everybody has to reset their passwords, right? That's much more painful for your users, right? But you certainly see that in almost every breach. They invalidate everybody's passwords. You have to reset them, those types of things, right? So how you go about doing the migration from a user experience perspective is kind of up to you as the developer of the application and the scenario that you're in, right? The nice thing about this particular construct, and the reason why we did this instead of just asking you guys to write a couple of lines that did a bcrypt thing, is that, well, you can figure out the bcrypt thing, no problem, right? I mean, just go find the documentation, it's pretty straightforward, right? The interesting question about this is, how do we set this up so that you have the flexibility going forward with your app to be able to handle all of the cases that you may run into in having to reset passwords? Whether it's right away, whether it's a migration, how fast does that migration need to happen? Right? Because a lot of times I'll go into a consulting engagement or something and say, okay, well, we need to migrate all these passwords. And it's like, okay, well, we'll have to take the web app down and then migrate all of these passwords or turn everybody off and they have to reset them. So, well, no, there are options. And if this is the scenario that you have set up, then it's a relatively easy code change to be able to support some of these types of things. So that's why this is a little more complicated than just having you guys go in and write some bcrypt stuff, because I figured almost everybody here is kind of capable of doing that, right? So.
All right, so now we've got the user model changed. The next thing we need to do is take a look at how we're actually querying to find our user. So as you recall, in the old model here, we went ahead and did a filter by username and password. So that obviously won't work because the password they're going to pass us is not actually what we're going to be storing in the database. So we're going to want to go, oops, that's a nice one. That's why. All right, that's better. All right, so what we're going to want to do is change that query to say query equals user.query.filter by username. So that's the way we're not matching on password. So once we've made that change, you may notice an interesting problem, which is that if you just keep going in the code, if not DB user, and we have a system that looks like this, well, that means that we're not actually checking the password at all, right? That would be a really bad thing to go ahead and do. In a well-written Flask app, you would actually have a test that tests for this. Unfortunately, this is not a well-written Flask app because I wrote it. But no, there are actually reasonable testing frameworks that can handle this sort of thing, and I really wish I had had the time to add it, and I apologize for that.
Well, it's like it's easy to make fun of these types of errors, right? Where it's like, oh, okay, well, all of a sudden you rewrite some code and then you're not checking the password. This stuff happens, right? It happens actually with reasonable frequency, because then the developer is going to fire this up and they're going to log in and it's going to work fine, right? And it's like, great, done, moving on. Right, and you saw this, and this is not to bag on Dropbox in any way, but you saw this in one of the Dropbox pieces where they're very focused on degrading their service in a reasonable way. It's awesome. That's one of the reasons why Dropbox works so well, right? But they had an error in that judgment where all of a sudden it degraded to the point where if you didn't have the authentication framework, it actually lets you log in. So for a very short period of time, you were able to log in as anyone on Dropbox. This was years ago at this point, I think. But these types of errors happen, and they happen in the best applications. And as applications get very, very complicated and you start to split up your authentication from the rest of your app and various other things, these types of things can happen, right? So the goal of this thing for us, for kind of walking you guys through this particular thing, and the reason why it's a little more complicated is so that you know what actually has to happen in the process so that you can kind of walk through it as you're writing the code, right? So, is it using the right construct? Is it checking to make sure that all of those things actually match with its username and password, and actually checking the database and making sure that it's being stored correctly? Because one of the things that we run into a lot when people are remediating applications is they'll make a change, test that it still functions, and then move on, but don't really test that you actually solved the underlying security problem. Like, you may have thought you did, right? But sometimes it's really hard, right? If you were using SHA-256 and you go look in the database, it just looks like a bunch of base 64 encoded junk, right? So how do you know that it's the right base 64 encoded junk, right? And so that's kind of why we went with this way, and as we think about kind of fixing the problem.
Hex encoded.
Well, that's base 64 encoded.
It's mostly going to be hex. All right, so the next thing we're going to actually need to do, so we actually want to verify the password, right? So we should probably go ahead and write a quick verify password function. So the verify password function is going to take a DB user and the password, and then it's actually going to check equality, which seems like it might be a bad idea, right? So unfortunately, well, fortunately, but a little unfortunately in terms of just the magicness, that equality is an override. Basically, the dunder equal method inside the object has been overridden and does special actual bcrypt comparison rather than direct comparison. So in reality, that equality test does not actually test to see if the passwords are equal. It tests to see if the bcrypt hash of this password, utilizing the salt that's present in here, actually does it. Fortunately, you don't actually have to think much about that beyond what I just said. You can go ahead and just say dbuser.password equals password. And then we have the last little bit of magic here, which is effectively that since we're doing password migration, we need to go ahead and update the database row if it's been changed. So inside this equality, it actually will change the password and dirty that object. You can check to see if that object has been dirtied. Session.dirty is a thing that exists inside SQL Alchemy. In this case, we made it nice and simple, and we just said we're going to update that row every single time. Obviously, for efficiency reasons, that's not necessarily the best idea in production, but it's much more discoverable in terms of how we're doing it right now. So we add it to the session, and then we commit it. And then we return true, because obviously if the password matched, we want to say true, and otherwise we want to say false. So once that's done, we actually need to use it now, right? So instead of saying if not DB user, now we want to say if not DB user or not verify password, DB user password. So once all of that is done, you should not quit what I just did because I'm dumb. That's okay. I guess that means I'm going to get to go ahead and create a new one. I never only keep one tab open. So Command Q is usually, or colon Q is usually safe for me. There we go. Not that. All right, so you should now be able to run your app again. And if you run app.py, it'll start up. You can then log in again. If you're already logged in, make sure you log out and then log back in. And if you then take a look at your database, you'll see that the password is now actually a big long string of nonsense.
Although less nonsense than you would think, right? So like bcrypt does a fun thing where it jams this at the beginning of the string, so you can recognize that it's a bcrypt hash, and then the work factor is actually stored inside of it. So that's how it knows how many rounds it needs to do. So remember we talked about 12 being the default. That's why it says 12 in there. And then of course the hash is what comes after that last little piece. Along with salt. Yep.
And that's actually all there is to it. That's a full remediation of a password vulnerability. If you had a system like this, as we talked about it previously, say they have 10,000 users, and you have 1,000 active users. Well, then 9,000 of those passwords are still going to be the old style, and 1,000 will be the new style, which of course is not ideal, as we stated previously, but gives you a significant improvement in security for those who are logging in. Those who are inactive, there's a variety of ways of handling that. You could potentially say reset their passwords, like force them to reset their passwords. You could also just deactivate their accounts over time. That's something some companies choose to do when they have long-term inactive accounts. They just delete them eventually after significant user warnings and things of that nature. So for anybody who has completed, I think this is probably a good time to go ahead and take a 10-minute break. For anyone who's not, we're certainly welcome to stay here, and we will continue to assist. Let's try and get back in here at 2:35.
We get started again. Great. So common question apparently. Paul's vimrc is on GitHub. So if you would like it, it's under Reaper Hulk, same place where the exercises are under a .files directory. It's all in there. So if you want to, spend the next 4 hours of your life trying to get Vim working the way that Paul does, you can do that. Yeah, it would be more than 3 hours. So let me put it that way. Yeah, it's quite, every time I watch him code, it just makes me sad that I am not that fast. And then I will spend like an entire day trying to do that and realize I spent 8 hours trying to get Vim working faster rather than actually, it's not like I write code anyway anymore.
Well, let's be honest, every month or two that happens to me too.
Just forget how to do things.
No, I spend like a full day trying to figure out how to make my environment better, and it means I lose any productivity I could possibly gain.
Yes. All right, so moving on. So we're going to talk about key management. So we're going to talk about a little bit of stuff, but I think what's interesting here is that this tends to generate the most questions from developers anytime that I talk about encryption or key management. And a lot of it is because it offends us, right? It offends the answers of how you do this and what is secure and what isn't secure aren't really great, to be honest. This is a very, very difficult problem to do well. And especially when you start getting into the really more advanced ways to kind of handle some of these types of things, you start getting into very expensive solutions around HSMs or hardware security modules and all kinds of fancy stuff. So we'll walk through kind of the basic of like what you need to know and how you need to do it to kind of meet whatever the minimum bar is to be secure. Right? We'll talk about that today, and that's what the exercises will be about. But if you have questions, if you want to dig into this, if you have existing systems that you try to do, if you have questions about how things plug into automation frameworks, various other things, definitely throw your hand up and let's talk about them. Because this to me is the one that usually people run into, right? All right, so we'll go through this real quick and then we can kind of talk a little bit. PowerPoint is, awesome. I don't know what you're talking about. Yeah. So
I've seen people do presentations in Vim. They are crazy.
Yes. Well, and much like Paul, every couple of months I try one of the PowerPoint alternatives, reveal or something like that, and realize that I can't do that and I need to actually do work, and so I don't. So before we get into the kind of how we store keys, we want to talk a little bit about randomness. There is a lot of misinformation about randomness that flows around. Especially this is the case for all cryptography, is when you start actually searching for it on Google, you get some serious crackpot stuff. And things move relatively quickly in crypto, and so you'll find old messages that are very popular but are actually no longer correct, and all these various other things. There's also a whole lot of neckbeard arguing that is very hard to get to the actual answer. And so we wanted to kind of address a couple of things that you will hear about randomness, because the story is actually much simpler than you think it is. So the first thing we're going to talk about is a little bit just about generating keys in general, right? So if you're going to generate an encryption key, right, you have to use a secure random number generator. This seems really obvious, but unfortunately a lot of programming languages and frameworks include both secure and insecure random number generators, and it's usually very easy to use the insecure one, and it's a little bit harder to use the secure one. This is mostly due to performance. Insecure random number generators are very, very, very quick. Secure ones are a little bit slower. That being said, I've literally never seen an application that could not have used a secure one rather than using an insecure one. Right, so whatever platform that you happen to be in, there is a secure random number generator, right? So you'll need to find it and use that if you are going to generate an encryption key. If you see yourself calling like math.random, you're probably in a danger zone, right? Which is fine, and it happens more than you would think, right? Almost every single one of these examples come from stuff that I saw when I was a consultant or whatever it is. These things happen relatively frequently, so don't feel bad if you've seen it or you didn't know, right? So anyway, so moving on, there are two things that you'll hear a lot about randomness. One is about virtual machines, right? And one is about dev urandom, right? So there is a lot of talk about entropy on virtual machines. And for the longest time, when an OS is generating entropy for you to be able to use as part of a random number generator, that it pulled entropy from various things that don't work as well on a virtual machine. So things like mouse movements and hard drive accesses and some of these various other things that were pulled in as randomness inside of the kernel. And so there was a worry, and it was true for a while when virtualization was first getting very popular, that it was possible to exhaust the randomness of a kernel, or to go and ask for data that you believed was random as a developer, but it was actually not random that was coming out of the kernel. So kind of to see the result of that, how many people heard about the Debian bug where they accidentally screwed up randomness for a while? So there was a commit where somebody accidentally made a code change inside the kernel that basically eliminated a lot of the randomness involved in generating keys, and thousands of encryption keys were generated over a pretty reasonable period of time using this code. And it turns out that those were trivially breakable once someone knew that once someone found the bug, right? So if you are pulling from a source that does not have enough entropy, it basically breaks all of the guarantees that you have around your crypto, right? And that's also true when you pull from non-secure random number generators, right? That being said, the state of the art around virtualization has moved significantly since those times. At this point, there is almost no chance that you will exceed any type of randomness required from a virtual machine in almost any environment. Yes, wide statement, so someone could probably prove me wrong if they really wanted to. But in general usage, if you're using a cloud, if you're using some kind of virtualization technology, don't worry about it. You're generally going to be fine. There have been changes made to the kernel, changes made to the virtualization layers, various other things to make sure that they expose that randomness as much as possible. If you really are concerned for some reason, you have a very weird use case. So something like having to generate umpteen bajillion random number generators within microseconds of the machine booting or something like that, then there are ways that you can seed your random number generator with randomness blocks. You can get those randomness blocks from a hardware security module like an HSM. You can also go buy a random number generator if you want. It's a little USB stick that you can stick on the back of a computer. And basically it pulls randomness from the radio waves that actually kind of float around all the time inside the atmosphere. It's float around, yes. If you want the details, go read about them. I don't care. Suffice it to say, you plug the USB thing and magic happens, so stop worrying about it. Anyway, but for the most part, you shouldn't have to worry about this anymore. So you still will see tons of this junk on the internet. You may run into security people in the security space who try to tell you that you can't do random stuff on virtual machines because, entropy. None of that's really true anymore. So luckily, technology is moving beyond that. Don't have to worry about it. The other one that you will see is a stupid neckbeard argument around the difference between dev random and dev urandom, right? So these are devices in Linux, right, that you can ask for randomness. And the theory is dev random is insecure and dev urandom is secure. Other way around, yes. It doesn't matter. Suffice it to say, it doesn't actually make any difference. So if you look in the man page for dev urandom, they will tell you that it is not secure. They are wrong, and they should change the man page. But there's a whole bunch of fighting about for no reason of why they don't want to change it. It doesn't actually make any difference. If you need randomness in Linux, and that is why the example is super, super simple, just ask urandom, and you're done. Right? All of the hard work has been done for you underneath the covers to actually make sure that there's entropy there, to seed it correctly. All that stuff is done. Right? It's far easier to just ask the OS for randomness than it ever is to try to generate it yourself. Well, that's a bold statement. You may disagree with me, but.
So on the bright side, it's not just Linux for this. When you call it os.urandom in Python, it's abstracting away the complexity. So actually on Windows, this is called a function called cryptgenrandom. On OS 10, it does open dev urandom, but dev urandom and dev random on OS 10 are actually the same thing. They're just symlinks, so that way that they're more compatible with Linux, essentially. So os.urandom will work on any platform Python runs on. It's what you should use for any type of key generation. It's what you should use anytime you need randomness, pretty much exclusively. Import random is a popular thing. Import random is not, as we discussed earlier, import random is not a secure random number generator. It's in fact Mersenne Twister. Mersenne Twister has an interesting property whereby if you observe 640 outputs, is that what 624 outputs. Yeah, you can guess earlier, but if you see 624, you know the entire internal state of it and can predict all future outputs. So all you have to do is see the output of it 624 times, less if you want to try and probabilistically guess it. Lots of cryptographic algorithms depend very heavily on randomness. Many of them should not, but they do anyway. As a good example of this, there's something called the digital signature algorithm, DSA. And there is a variant of that called the elliptic curve digital signature algorithm, ECDSA. So when Sony made the PlayStation 3, they said, well, we don't want any random people to be able to flash firmware. So we're going to sign it with an ECDSA certificate, and we'll keep our private key in an HSM, and no one will ever be able to get to it because it's obviously secured. And so then we'll just sign new firmware packages whenever we need to, and we'll distribute those out to our customers over the internet. And because we've baked in that certificate into the Sony, into the PlayStation, it can then verify that that firmware is valid. That's all fine, but the way ECDSA actually works, it requires a K, which is a random number. It doesn't actually have to be random, but in practice, it has historically needed to be very random, and it very much can never be the same. Sony made it the same every time. And therefore, all it took was 2 signatures, and you could recover the entire private key. So if you ever wondered how Sony ended up having the PlayStation 3 get hacked and how all the custom firmwares and everything else came about, that's what they did. They made an elementary crypto mistake that compromised their entire private key for all time for the PlayStation 3.
Yeah, and we've mentioned a couple of times companies that have had various problems. This is not to knock on them. This stuff is actually hard, right? The people who designed the PS3 actually weren't idiots. That's actually the right solution to the problem that they were trying to solve. They just made a mistake, right? And so that's partially why, one, we focus on teaching things like this. I think next PyCon we're talking about doing an advanced one. And 2 is the separate pieces. As we're building more and more of these crypto libraries, we're trying to expose them at a higher level so that you don't have to make those types of decisions, right? So when you look at bcrypt, it's a very simple interface to be able to use, even compared to PBKDF2, right? And so we're trying to take a little bit of the decision-making away, because in the most case, you actually don't care about all the bells and whistles and knobs, and really it just makes it a lot easier to blow your toes off, right? So like, it's not to knock on any of these companies that have made these mistakes. I'm sure I have made these mistakes in my previous, code when I didn't know what I was doing. So we don't want to bag on them, but we do make these mistakes, and they are interesting to. The reason why we point them out is because a lot of this stuff seems esoteric, but big systems rely on all of these things, and there are guarantees, and those guarantees are based on assumptions. And a lot of times that's the part that we don't get to as devs. We kind of look at, oh, hey, here's how the code needs to work, and I go and I write some code, and it works, and great, I move on with my life, because we don't have the time to learn every single tiny little technology from first principles. The problem is that if you don't know those assumptions, then you build systems that actually don't work, right? And even people who spend an enormous amount of money, trust me, like making sure the PS3 was not able to run copied games was #1 on their list of things that they had to do when they launched that platform, right? Probably one of the most important features they wanted out of it, and that simple mistake broke it. Right. In addition to a whole bunch of work that GeoHot and Failoverflow and all those guys did, but.
And another big part of the problem is like getting it right looks exactly like getting it wrong. Like if you get it wrong with anything else, like if your ORM is misconfigured or whatever, you're going to get some exceptions and your website isn't going to work. If you get your crypto wrong, it looks exactly the same like if you got your crypto right, and it's virtually indistinguishable to most people. So again, in their defense, like they're clearly not idiots. They made a mistake, and unfortunately,
So this one is well outside of what we're actually going to do, so I'm only going to spend a few seconds on it. But if you're actually curious about breaking Mersenne Twister and also recovering a DSA private key, I have a little game that's sitting on my repo. It's under reaperhulk/DSA-CTF. And it takes the structure of messages, emails that you can then read through to determine how to actually accomplish the task. Basically, a little capture the flag to recover a DSA private key. That is, however, a topic for your own time. Okay.
I think we're at an exercise, yeah. All right, so time to jump back into code.
So for the storage exercise, what we're going to go ahead and do is you can see inside the IRC channel, the exercise 2 cheat sheet is available. But effectively what you're going to do is cd into to data at rest start. Believe it or not, even though it says data at rest, we're not actually going to do anything with the data at rest just yet. At which point you're going to want to look at, we can take a look into the application. You're certainly welcome to start running it. If you start running it, you'll see it looks suspiciously similar to the previous application because it actually just builds on it. So if you log in, the admin password, this time you'll see an upload dialog, which you can choose to upload a file or not. If you choose to upload a file, let's see here, what should I upload? Some random thing. There we go. A random piece of the PKCS11 spec. Ooh, that's a good UI right there. That's because it didn't upload. Nice. Turns out somebody just didn't handle a lot of errors here. Yes, so if you choose to upload the file, it'll save, and then if you choose to download it, you will see it download back, and in this case, it is a whole bunch of disgusting C.
Yeah, so we've chosen here an example of protecting a file that a customer uploads to a site. This is a relatively common thing that we have. So this could be anything from, tax information to whatever, piece of information that you want to protect. That being said, this doesn't have to be a file, right? This could be data that they type in. This could be obviously images that work in the same way. So basically any block of information that you want to protect, and then store that protected information in a database, right? So obviously there are other ways that you can go about protecting data at rest, lots and lots of different ways. We just chose this one because it's relatively common that you have some piece of data in an application that you want to protect. And in this case, we're actually, again, starting with an app that functions in an insecure manner now where that data is not protected, and we're actually going to go and add that protection on top of it.
So before we actually even get to encryption, we have an interesting problem with our key management, right? So if you look, we have that app.secretKey equals I am really secret. So I've got this in GitHub. You guys obviously already got my secret. That's clearly a problem. So let's go ahead and do something to remediate that. So there's two ways we can remediate this relatively simply, right? We can write it to a file, and that file can either just be its own file, or it could be a config YAML, or it can be an ini, and you can choose what you want to do in that regard. In this case, we're just going to use a bare file because it's the easiest code to write, although obviously you can import PyYAML and do whatever you'd like on your own. The other way we can do it is with an environment variable. So in general, environment variables are available on Linux and OS X, and even inside Windows shells, actually. What they do is they allow you to inject key value pairs into the environment, and then those can be fetched from Python and read. So the first thing we're going to do is go ahead and implement it as a, excuse me, as a file. So we're going to replace app.secretKey with a with open, which for those of you who are maybe not familiar, if you do with, that's a context manager, which will auto close the file when you're complete. So you don't actually have to hold on to the file handle. You don't leak that file handle. It's generally just considered a best practice thing. So we're going to create a secret key.text, or rather we're going to read a secret key.text as f, and then we'll set app.secretKey to equal f.read. And then we don't need this line anymore. Of course, if we save this and try and run it right now, obviously that's going to raise an exception because secret key.text doesn't exist. So we need to go ahead and make sure that we actually get the I am really secret. And we'll do that with, I'll just do it over here. So you can save that secret key.text as I am really secret. And now if we try and run that code, the app starts up. I can sign in. And all is well.
Everybody able to get that working? Should be relatively straightforward. So the first step for this is like one of the options that you can do, obviously, is move this. So anytime you see a key or a secret element or really any type of configuration at all hard-coded in a file, this is bad news. Most of us know this already, right? This isn't magic. This has been around for a long time. And so a lot of times I'll get questions where it's like, okay, well, if I want to store a secret value, do I just put it in the config file like I do with a lot of other stuff? And the answer can be yes, right? That's not necessarily a bad thing. There are various other ways that that may not be allowed for the particular application that you're talking about, right? So if you're talking about an encryption key that is not allowed to be written to disk in an unencrypted manner, well, now you have a secondary problem, right, where you can't actually store that in a configuration file, and you may not be able to do that, right? Or if you don't want that key or that secret ever written to disk at all, right? There are other ways to kind of handle that. But for a lot of applications, storing it in a configuration file, especially if your particular web framework kind of offers a secrets configuration file that you can use by default, right? Rails does that. I think Django does that now. Don't know if it does off the top of my head, but certainly Rails does. Then that's an easy way to do that, right? When you look at something like .NET, for example, there's ways to actually encrypt you can put it in a configuration file, and then you can actually encrypt the piece inside the config file, so you can do it that way. But there's nothing inherently wrong with doing that, right? I get a lot of questions from people who's like, well, okay, well, clearly I can't just write it in a configuration file. Well, you can. Now, you have to be careful about where that configuration file is, how it can be edited, who has access to it. If somebody's checking that configuration file to source control, go track them down and beat them with a stick, right? But it certainly is one way to kind of go about protecting those things.
All right, so the next one, and in fact the last one, is going to be going ahead and getting it from an environment variable. So one of the most common, you'll need to import OS, but as you already know, OS is imported inside this file. So all we really need to do here is app.secretKey equals os.environ, and then we'll call this secret key. Incidentally, I'm not using .get because I want an exception if you don't pass this. So in this case, that's all there is to it. If I try and run this right now, it's going to blow up on me because there's a key error. I didn't pass secret key. So what I need to do is pass secret key, which I am really secret. I can't remember what my secret key was now. Yeah. I am really secret. I know, I couldn't remember it. And there we go. We're up and running. And if I try and log in again, here we go.
You're not really encouraging that, though, right? Because now it's in that history.
Yes, so I was about to actually say that. So obviously the problem with doing it this way, as was pointed out here, is that when you do this, it's now in a bash history file. And that's probably a whole lot worse. Yeah, and it will show up in your process list and a variety of other places. The correct way to do this is there's a way to inject, there are several ways to inject environment variables where you don't do those sorts of things, where you inject them directly into the process. Those are the ways you absolutely should do this. Unfortunately, that requires a survey of the concepts behind shells and a bunch of other things, so that was kind of a little out of scope. Suffice it to say that in general, environment variables are actually a very good answer, with the occasional interesting exception of things like shell shock. For those who are familiar, Bash had some interesting problems with the way it escapes environment variables. Those are not necessarily directly a problem for this, in that environment variables, those are ones that were untrusted by the, like basically they were being interpreted by the web frameworks or what have you, and then directly injected automatically without like an administrator's control. So you control all these variables, so it's not really a big problem. Although sometimes those variables become readable if you have shell shock.
And there are some specific issues with the environment variable piece of things. If you're not very careful, if you p-open a process or if you create sub-processes off of it, then by default processes inherit the environment variables of their parents. And so that can be dangerous. Say you're using IconV or something like that to do some data manipulation stuff or some image manipulation stuff, then you may run into stuff where that process now has access to the environment variables of the parent process. There are certainly ways to get around that, right? You can pass flags to not do those types of things. But in general, when you look at most web applications, there's not really a huge amount of risk there. And so it's generally the easiest way to throw those things. This also allows you to write code where you may not have to have that password or that particular key written to disk anywhere on the server at any time. And that can be very nice, right? That being said, if you have application level vulnerabilities that allow people to enumerate your environment, then you will see, they will be able to see those keys, right? So you have to be careful about that.
One last thing to note here is that, excuse me, so I went ahead and said, oh, we should remediate this. We should remove that key from the Git data, or from the Git history, and move it out. Well, you can't really do that. Like, I mean, we could go back and we could try and delete Git history and we could force push and whatever, but somebody else has probably already cloned that repo. I don't know, 46 of you, and you probably have access to that secret now, and that's a big problem. So in reality, if you ever see this, don't just pull it out of the config file. You need to rotate it. You need to change that secret. It is no longer secure. Anytime you make a change of this magnitude, it needs to completely change. So yeah, that's where we're at.
Yeah, I think it's worth noting in general that as you build cryptographic systems that rely on secrets, you will have to change the secret. You will. It will happen, guaranteed, right? And so we run into a lot of systems where over time, the scale and the assumptions that were made when the system was built make it very, very difficult to rotate the key. That makes it very, very brittle. So as you're building these types of systems, build in a way to be able to rotate keys. And we can talk about that if we have time, but
we're going to show them a system that we don't do that.
That's true. But anyway, so from a history perspective, from a compliance perspective, from a breach perspective, it is very, very likely that someday someone will come and ask you to rotate every secret that you have inside your application. It needs to be easy to do that, right? If it's not, you will have a very bad day. Right? Anyway, so we're going to jump into data at rest. So anyway, before we move on to data at rest, key management is relatively short for us, but I just wanted to make sure, like, any questions that you guys might have that you want to talk about, any concerns about that particular approach. Like, these are relatively simple. We kept it simple. Of course, you can get fancy with putting keys in HSMs and storing secrets on a third-party server or various other things.
Do you have a recommendation for that, the latter, the storing secrets
in an HSM? So, yes. So we actually, one of the products that I started at Rackspace is Barbican, which is the key management platform for OpenStack, which basically does exactly that. So it's a REST-based interface that sits on top of an HSM for all intents and purposes. The challenge with doing that is every time you offload a secret to a third party, you're now introducing an authentication problem between you and the third party that owns your secret, and the authentication credentials become the new secret, right? So all of a sudden now I'm storing your secret data in an HSM and it's all encrypted and no one's going to be able to touch it and it's pretty much guaranteed that no one can touch it. But now you have authentication credentials sitting on your app server that allows you to retrieve that secret. So as an attacker, all I need is the auth credentials and I have it. So it becomes this Russian doll problem where like you can keep protecting keys with keys and keys with keys like all the way down, but sooner or later there's going to be a key somewhere in plain text that someone needs access to be able to do a thing, right? So HSMs get super valuable when you talk about signing, in certain types of encryption things where you want to be able to encrypt data and ship it out. That can be from an asymmetric perspective. If you just wanted to store a secret in an HSM, it's probably not going to buy you a huge amount of extra security. Now, it can make it a lot harder for an attacker to figure that out. An automated attack may not work against you now. Someone's actually going to have to spend some time and look at your code and figure out how it works. So, Alex Stamos, who's the CSO of Yahoo, has coined this great term called security nihilism. And it's this theory that a lot of us in the security community get to the point where it's like, well, you can't protect against all the attacks, then it's not even worth doing anything, right? Just why bother? But the fact is that putting some level of protection in place, even if you know an APT attacker that has access to your code and spends the time to do it will still be able to break it, you're still going to reduce the risk that you have to your company significantly, right? So shipping those things off to the side can certainly help. It also makes your system more complicated. Right, your deployments are now more complicated. You have dependencies now for your apps booting and various other things, and so there can be operational costs in doing that.
The level of key management complexity you go into is also going to be somewhat predicated on your audit requirements, really. So, like, if you get popped and it's living directly on the server, and they obtain that secret, and then they go and do something with that secret, there's a good chance you're not going to know about it for quite a while. If you do choose to go down the Russian doll problem a little bit and you put something like a Barbican or some sort of other system that your configuration management loads the secret onto the system, that system then reaches out to ask for the actual key, there's some interesting ideas you can put around that. At the very least, you can put around audit logs that say, well, I know it only came from this point, it came at this time. Potentially, you can actually tie that into your boot processes where you can say things like, this VM boots and it immediately starts the service, so only for the first 3 minutes of that after that boot where I've notified this service will I actually allow you to fetch that secret. So no. Oh yeah.
So there is one. So there's a startup that's working out. So basically what they're doing is they're offering everybody royalty-free licenses for dropping miniature HSMs on any piece of hardware that you build. This is not something that almost like Rackspace can do this, Google can do this, Facebook, this is we're building a bunch of hardware. And so it allows you to drop the extent of a tiny little HSM on any single server that you build for about $10, right? And the nice thing about now that what they're selling is the software that actually starts to orchestrate all those things. But then you basically get an HSM everywhere. And those HSMs now allow communication between them in a very secure fashion and some of those types of things. And so you do get into like, okay, well now I can always store my secret in an HSM local to the machine that I'm on. I can audit it. I can do various other things. That's not really available to the general computing public yet. You will see that, right? In the next couple of years, you'll start to see that stuff. But right now, it's still pretty avant-garde, and I'm not even sure if these guys are going to be the right guys, right? It's just I know that they happen to be doing that right now. But yeah, I mean, I think the value to offloading it to a third-party system right now is that immediately you get an audit log, right? And even if you don't build any system of that, you can sub that audit log to your security team and their SIM, and they can start looking at that. And it's like, okay, well, you can start doing things like, hey, if I see an access to the secret, I can go and check the uptime of that server, and if it hasn't rebooted, then that should fire an alarm, and I should go check it out, right? I mean, the other problem, like right now, the average time for a company from when they were breached to when they detect it is 223 days. Right? So it's an enormous amount of time when an attacker's in your system basically doing whatever they want. If you can shorten that at all, it's worth it. Right? If you can get it down to like half a day, right, or even hours or minutes, I mean, this is what the best people in the world are doing. Right? You will get breached. There's no question about it anymore. Right? Like protecting them, keeping the barbarians out of the gate, not going to happen. They're going to get in. The key game these days is detect and respond as fast as humanly possible. So if you can build some stuff into your app that shoves this stuff over to your security teams, and they can start to do some detection on that, not only will they love you, and having your security team love you makes your lives a lot easier, but you also get some serious value out of that stuff, right? In that, yes, they're going to get that value, but if you can detect, respond, and move it, especially if it's an APT where they actually have to figure out how your network works and how your app works and all that stuff, they're not doing that in 2 hours, right? It takes them a long time to figure that out. When you look at the target attacks in some of these companies, I mean, these are things that happened over, weeks and months for time frames for these types of things. So certainly value in that, but again, you have to balance that with how complicated is the system, how expensive is it going to be, what are my uptime requirements, and the impact for those. So. Yeah, we got to keep moving. All right, so moving on to data at rest. So now we'll talk about protecting some data that's been written somewhere, whether that's a database, a disk, whatever it happens to be, but it's disk or data that you want to persist, right? So there's 3 general ways that we'll talk about protecting data. So the first is hashing. We've talked a little bit about that so far, but we'll talk about that. And then we'll talk about symmetric and asymmetric encryption. So when we look at hashing, right, people always kind of question, well, how is hashing encryption? To a certain extent, it isn't, right? Hashing is destructive. So at the end of the day, when you hash data, it's gone. You can never look at a hash and reconstitute the data from it, right? And you can, this is intuitive when you look at it. The output of a hash function is always the same size, right? So if you look at SHA-1, it's 160 bits. I can hash 4 petabytes worth of information, and that hash will be 160 bits. So I obviously can't reconstruct 4 petabytes of information from 160 bits. Otherwise, it would be the world's greatest compression algorithm, right? So hashing is destructive, right? But it can be very valuable for us because now there is no way that you have the secret data, right? So where this is really valuable is if you need to store a secret that you can compare, right? So passwords are the obvious option, right? So when you protect them with a KDF and all those types of things, at the end of the day, you're not storing the password anymore. So if you're breached, you don't have it, right? Which also means that you're out of scope and various other things. If you need to store a credit card number and you can hash it, right? If you can destructively hash it, you're not in scope for PCI, right? It's not always true, but in general, that will be true. Like the #1 way to keep yourself from getting in trouble in a data breach is don't store the secret information in the first place, right? So don't have it, and if you do need to have it, if you only need to verify it, then hash it, right? Because that way no one can ever say that you could reconstitute the data, you don't have access to it. So, you know, whenever you call your cable company and they're like, hey, we want the last 4 of your social, which they should never be doing anymore, but they still do that, they're not storing your social security number, they're hashing it, right? And they're just comparing it. So you can never get the value back, but you can compare to see if it's the value is the same as the one that you got the first time. That make sense?
Although it is worth noting that with the last 4 of your social, there's only 10,000 possible combinations.
Yeah.
So we already saw how fast you can do hashes.
That's true. Generally, they only use that for phone passwords and stuff anymore. But anyway, so hashing is relatively straightforward. Do we have a demo for this? No. So we'll just, yeah.
All they do is compare the hash, then would you not know the hash would be a way of compromising that? Like if someone listening to my phone conversation knew the last 4 of my social, they don't know my social, but they can use that last 4 to still call Comcast.
Yeah, I mean, at that point, they have the key, right? So if they know the last 4 of your social, they'll just call Comcast, tell them the last 4 of social. They don't care how Comcast has protected it. What matters here is that you're Comcast, right? If your database is breached, right, you can legitimately say to your customers and to the federal regulators and to the people who are suing you, I didn't have the data, right? So, you know, when you look at Target, for example, right, Target's out, I think the last I saw was about $440 million for the breach, and they're still being sued by everyone who is actually compromised. So if they had hashed all of that data, right, in this case let's ignore the fact that would have been impossible, but if they actually were capable of doing that, they could legitimately go and tell that court, we didn't have the data, right? Yes, that data was breached, the hashes were breached, but there's no way to reconstitute that, and so the appellants have no standing and you walk away, right? So the 2 places where it matters a lot, 1 is reducing risk for your company from a being sued perspective, and 2, reducing scope from a compliance perspective, right? If you don't have the data, you don't fall under compliance. Right? And that means that you don't have to do the 9,000 other things that the compliance regime is going to want you to do. Right? The #1 thing in compliance is scope. Hashing reduces scope. Right? So this is very good if you can get away with it. But again, this means that you don't need to do any computation with the data. Right? It just means that you're comparing it. So it's relatively simple. So in this case, we're using hashlib, which is built in. And so we take a password. In this case, we're using SHA-256. Now, before, remember, we were talking about protecting passwords, right? We're talking about using bcrypt and various other things, right? And so you generally want to use those for pretty much every time that you would use hashing to protect a piece of data. I don't think there would be a main reason to do it. So the only reason you would use fast hashes is generally if you're looking for integrity, but no security, right? So if you're looking to make sure that a file hasn't been modified or something like that, then it could be fine. All right, so moving on to symmetric encryption. So this is one we will do a demo on, but so symmetric encryption, there's 2 types of general encryption, right? Symmetric and asymmetric. And these have the property that's different from hashing in that, yes, you can protect some data, but you can also get it back out, right? So you can reconstitute whatever that protected data is so that you can do computation on it, right? So before we use the example that we started looking at of protecting a file, right? At that point, if you never need to get that file back out again, then sure, hash it. If you just need to compare it, if they give you the same file every time, fine, right? But generally, if you have a file or you have a piece of data that you want to protect, you want to be able to get that data back out so that you can do interesting stuff with it, like a configuration file or something along those lines. So for a symmetric encryption piece, it's a function that uses the same keying material for both encryption and decryption, right? That's why it's symmetric. It's the same key, right? What that means is if that key is compromised, that's the ballgame, right? Like that key is all that protects the data that you have encrypted with it, right? So the places where you want to use symmetric encryption is when you need to protect some data inside of your application that you are not going to share with anybody else, right? So being able to take some data, encrypt it, toss it in your database, pull it out of your database, decrypt it, and do something with it works great, right? If you need to pass that data to a third party, if you need to send that encrypted data back to the user, right, or any of those types of things, symmetric is generally not what you want because, again, for anyone to use that data, they have to have access to the key. And if they have access to the key and that key gets out, you have problems, right? So generally, you only want to use symmetric, pure symmetric, if you own that entire process, right, and you're not sharing that key around because key sharing is kind of a pain in the butt. But we'll talk about that in just a sec. All right, so time to jump back into code.
All right, so we're going to actually use the exact same data at rest start application we were previously using. So we've got our guy here. At least I think we do. Yeah. Excellent. And once again, just like always, we've got the cheat sheet is available. It was put into IRC. And I will answer that question momentarily. I'm sorry about that. So inside IRC.
How you answered it after you answered it.
I think in text now. So this is the exercise 3 cheat sheet. So for anyone who wants to follow along in IRC that way. Otherwise, what we're going to do here is if you look down in this application, as you already saw, we downloaded and uploaded a file earlier. You can look at these routes, and we have a download route that takes a file ID, filters it, fetches the user ID. This makes sure that you can't get a file that another user uploaded. That's a common mistake that you'll see inside these types of applications. They require a login like this, but then they just let you fetch anything. So you always want to make sure that you also verify that it's matched to the user. So this app already does that, so that's great. It does a very basic check to say, well, if you're giving me an invalid ID or whatever you gave me, then it's not going to give you a valid response. Otherwise, it returns the payload with status code of 200, sets the MIME type to what was in the database, and then uses some fancy content disposition stuff because HTTP is impenetrable nonsense. And then that's how you go ahead and download it. On the upload side, very similar. It grabs the file data. This is actually something that Flask provides for you. This requests files file data that gives you a little bit of friendliness. Basically, it provides you a stream IO, so we call .read on it to get out all the data. The file name, which was the file name that was originally uploaded, and the MIME type, which is a MIME type detection algorithm. So this is the very primitive MIME type detection that you see inside Apache and others where they map just a 3-letter suffix to a MIME type. So if you upload a .text file, it'll know it's plain text, even if in reality that's actually a JPEG. And then finally, obviously, during upload, we add it to the session and we commit it, and then we just echo back out some data that tells you where to download it. So if you previously uploaded a file, if you actually hop in and look at the SQLite, you can select from encrypted file, and you'll see this little bit of stuff here. In my case, I uploaded a header file from PKCS11, so you can see that it was just a bunch of plain text. And as you might imagine, your assessor has come along and they are displeased with you. They don't like the fact that you're storing all these user secrets in plain text inside your database. And so you tell them, okay, I've heard of this encryption thing. I'm going to go ahead and encrypt all those files, and we're going to store a key somewhere. So to do that, there's a few ways we can go about this. So symmetric encryption is a wide and varied subject, and there are basic encryption primitives like AES and DES, which is the data encryption standard, by the way.
Where's defense encryption?
Nah, it's data encryption.
I'm pretty sure it's defense.
Data
Definitely
encryption.
data.
Yeah. So there's AES, there's DES, there's Blowfish, there's Twofish, there's Serpent, there's a million different things. There's Rindal, which is actually what AES really is, which is probably pronounced wrong.
No?
I got it right? Excellent. So how do you choose that? Well, you can go a few ways. If you want to go the conservative way, then AES is the correct choice. If you want to go the Daniel J. Bernstein way, then Cha-Cha-20 is probably the correct choice. However, in reality, you shouldn't even be choosing from these. If you start thinking about these things, if you start thinking about, well, do I need to use cipher blockchain mode or Galois counter mode or all this, you're already in a lot of trouble. You're down deep in the weeds, and the probability of you making a mistake is very high. The reason for this is, in a regular, if you just encrypt some data, say I went ahead and just encrypted a few blocks of data, and I know, like as an attacker, I know that you encrypted that data and it was a HTTP header. And that means that I know the structure. I don't know what's in there, but precisely, but I know the structure of it. I know that it was probably a GET, which means that inside the HTTP headers, there's GET. Well, I can actually change that. And the reason for that is because of the way encryption actually works. All I need to do is XOR that particular byte. Knowing that it's a G, I XOR it with the value of G, and then I XOR it with the value I want it to be. And even though I don't actually understand what the encryption primitive was, I can change that G to anything else. So I can change from GET to MET to TET to whatever I want it to set. Those are all easily done. The decryption will proceed. You will never know I did it. So the way you avoid this problem is you add authentication to your crypto. There's a few ways to do that too. So you may want to do it with an HMAC. You can do it with asymmetric signatures. And so as you can see, you just keep going down this rat hole where there's more and more complexity just to get a basic safe crypto primitive. Or, and then this is the reveal, you can just use a thing called Fernet. So Fernet, which lives, I will actually drop this into the IRC channel as well. Fernet is a recipe inside of a library called Cryptography, which, full disclosure, I am an author of. Fernet was developed originally at Heroku. They use it to secure a bunch of internal object communication effectively. Its design is to be a one-shot encryption algorithm. Essentially, as long as it's a smaller file, where small is as much memory as you're willing to consume, you can encrypt it, get back a token, and that token is the encrypted payload, and then decrypt it later, knowing it has not been tampered with. This takes care of everything for you. You don't need to know what it's using underneath the hood. It's versioned, so if you ever need to change it in the future, it will automatically be able to upgrade. You get all of it for free. So we're going to go ahead and use that actually to implement our encryption. So the first step of doing that sort of thing is going to be that we need to generate a key, and we're going to have to pick a good place to keep that key. So to generate a key, there's a few ways to do it. I'm going to go ahead and hop into an IPython shell. IPython is installed inside your VMs if you'd like to play with it. So from that, I'm going to do from cryptography.fernet import fernet. And then all you need to do is type fernet.generate key. And it outputs this nice little base64 encoded key. In reality, this is 2 keys, but you don't really need to know what's going on inside of it. So I'm just going to copy this key. Nobody write it down. And in this case, I'm going to go ahead and implement it as, I'm just going to save it as encryption key.txt here inside my file. So then from there, once you've got that, I'm going to do with open, what do I call this? I can't even remember.
Encrypted key.txt.
Enc key.txt. I did actually remember. So just like our key management exercise, we're going to we write the key to a file, and then we load that key as the name key. So our next change is we don't actually have to make any changes to the encrypted file. As you notice inside payload, it just says large binary, which means it can accept pretty much anything. And then the way Fernet actually encrypts its tokens, it does not actually leave them binary. It base64 encodes them. That's just to make it easier to transport them over a variety of mediums. Fernet was designed to be able to transport over HTTP without playing any games with weird chunking. OK, so then I suppose I should go over here. So the next thing we're going to want to do, now that we've got all that set up, we've got a key, but we haven't actually encrypted anything. So we should probably go over here and implement it inside our uploader. So our original uploader had an EF encrypted file, login current user ID, and then here it said, I believe it said file.payload, which I can check. So I should look at that. File.streamRead. So instead of file.streamRead now, we need that to be token. And the token that we're going to generate is by creating a Fernet instance, passing in the key, having the encryptor here, and then calling encryptor.encrypt on the file stream. And then we just save it just like normal. And then over in download, we'll do a very similar thing where we grab our result, create a decryptor, which is again passing a Fernet key to create the object, calling decryptor.decrypt on result.payload, and then importantly, making sure that you put the decrypted data in the response rather than the encrypted payload. And then because I didn't mention it previously, you're going to want to make sure that at the top you've got from cryptography.fernet import fernet. Without that import, you will obviously get some import errors.
Yeah, so as Paul kind of mentioned, there's a huge amount of complexity in choosing how to protect a piece of data. The nice thing about Fernet is it makes all of that go away, right? So you saw, I mean, the actual encryption and decryption functions here are literally 2 lines of code. And underneath covers, there's actually a lot happening. Like Fernet is deciding what algorithms it's using, it's deciding key sizes, it's deciding how those algorithms will be combined, it's it's applying an HMAC, and it's signing things, and it's verifying that the data is protected both from a leak perspective. If you look at it, it's encrypted, you can't see what it is, so it's confidentiality protected, but it's also protected from an integrity perspective, so someone can't come along and modify it, right? It also gives you some underlying protection against having to be able to make changes to the algorithm going forward and various other things that it gives you. Right? So we could go through all that, but the easy thing to remember is basically if you're typing AES into your code, you're probably already at too low a level. Because once you're there, there are a lot of decisions that have to be made to be able to actually get a construct that does what you actually want, which is basically just boxing a piece of data and unboxing it later. Right? That's what we actually want from a development perspective. We want to protect some data, we want to get that data back, and we want it to be secure. That's what we want. Right? And so rather than getting down to that low level and spending days and weeks and months trying to be correct, right? This is an easy way to do that, right? And as LVH was talking about earlier, the problem is that when you encrypt something with AES, you've only solved like 10% of the problem, but it's going to look like you're done, right? Because at the end of the day, when you log into the database, it's going to be a whole bunch of junk sitting in the database. It's going to look encrypted. Okay, done, right? Like protected, right? And it's not like a lot of times the auditor, your security team, whatever, they may not get into it enough to know that it's not done, right? So this is an easy way to just duck all of those problems. Yeah. Pretty much.
As long as your file is small enough that you
yeah.
So because the algorithm for the signing, So because the algorithm for the signing is done across the entirety of the file, and you don't know if that file is correct until it's completed the processing, you don't want to do this on very, very large files. So very, very large files have their own sets of problems. So like this would not be a good solution for encrypting a 80 gig disk image. You're going to regret that unless you happen to have 160 gigs of RAM.
Yeah, so like it's going to decrypt that entire thing in memory, hash the whole thing, like all that kind of stuff's going to happen under the cover. So for small bits of data, this works really well. For very large bits of data or data where you want to stream. So a typical example here that we've been dealing with is how do you stream data out of something like an Amazon S3 or a Swift instance from OpenStack, right? So you may have a 2 petabyte file that you're streaming, right? And the problem is that you're decrypting every block and you're sending the user the decrypted block. And so they're getting all of that data. Well, they're not actually going to know if that data was tampered with until you hash the final block. So they're going to get 2 petabytes of data before they find out, oh, well, hey, I can't, somewhere in that 2 petabytes, something bad happened. I don't know where, right? I don't know when, but I had to download an entire file before I could find out. So if you're streaming something, very big files, Fernet's not a great great thing. But for tokens, small pieces of data, files, images, any of these types of things, generally fine. Makes it very, very, very easy. Solving that kind of streaming problem is actually an active research area that a bunch of us, well, not necessarily research, but a crypto engineering area of actually building a construct that's this high level that solves those problems. And we have some ideas on how to do that. We haven't written it yet, but you know.
Hopefully this year.
Hopefully we'll do that soon. But yeah, in general, this should solve probably 95% of the problems where you want to toss some data between, you know, a database and those types of things or write it off. You know, usually we'll solve most of that. So.
All right, so now if you've got all that done, you should be able to start up your app, which I will try and see if I can start up my app. Actually, I'm going to cheat and just actually run it from the solution. I know that works. Actually, do I? Yes. Yes, I do.
Your key's not there anymore.
I stored that in a crappy way in the solution. So I've got that up and running. So I go over here and I go to my login. I log in with my password. I choose a file to upload. This time I want to upload. Who knows what I want to upload? Let's upload the bootstrap zip. That seems like a great idea. I love how it doesn't work the first time.
Upload the source of your own thing.
All right, so we upload it. Oh, look, it's saved. So we download it. Got this nice little zip. Oh, look, it unzipped, no problem. But now we're going to go look at the database. And there are a whole lot of encrypted bytes. So there you go. Yes? I'm sorry? So in the as we were writing it, it was going to be a with open. In the actual solution, I cheated, and we can show you what the solution file actually looks bad. The solution file does it the bad person way, which is basically it keeps it right here.
So they're two separate problems, right?
So it depends, and I'm sure Jarret's going to want to talk after this since I had to take the mic from him. But it absolutely depends on your use cases. In many cases, you won't actually have a per user key, but you do want to be able to rotate it, which means you're probably going, like as you saw, what we actually had inside this for our, where's that object? This encrypted file object. We have a user ID, a payload, a file name, and a MIME type. What we probably should also have is a key ID. And the key ID maps to something that lets you identify where you should fetch your key from. That way you can rotate that key in the future, and that way you know which ones are encrypted with which keys. There are many cases also where you may want to do it on a per user basis, absolutely. And you can control that obviously in the same way. You just set your key ID, or you can, I mean, your data model is however you choose to make it.
Yeah, no, I think Paul pretty much covered it. I mean, at the end of the day, this is going to depend on what type of protections that you want. And one of the things that you can run into is kind of building some Rube Goldberg-esque set of keys that protect other keys that are user keys that whatever. But at the end of the day, it all, like, if someone has access to your database, then you're done. Or if they have access to that configuration file that stores that key, then you're done. So beware spending too much time on doing this stuff. At the end of the day, when you've encrypted something with the key, that key is the only thing that you have to protect. Right? So if at the end of the day you have a different user key for all of them, those user keys are stored in the database and they're encrypted with a key, well, all you did was move the problem back one layer, right? And there can be some benefits to that, but every time that you do those layers, you're adding in complexity, operational challenges, monitoring challenges, and all the things, and it's cognitive load on top of your system. So when you bring another developer in, they have to understand the Rube Goldberg-esque thing that you have built over time. And generally, complexity is the enemy of good security. So the enemy of good software in general, right? But especially in security, as it becomes hard to reason about, right? So you definitely can, in this case, when we're really talking about using symmetric as protecting data that you own that you're never going to give to anybody else, per user keys is not necessarily something that offers a huge amount of security. You may get pushed into doing that anyway, right? If you want to be able to tell your users that they have, each key is separate for each one, or, or if you have keys that are separated in different storage areas or whatever happens to be, it may make sense, but it'll depend on your app at that point.
Yeah, one last random one is that I have seen in the past apps that I've investigated where they had per user keys and they stored those keys in the database, which is the same database they stored the encrypted data. that is not of a huge amount of benefit, right? So the threat model you're protecting against and things like this is that your database maybe lives somewhere else. Like you've got an app server, you've got a database server. Maybe there's a scenario where you expect the database server might be able to be compromised while the app server is not, or the app server. As long as there's separation, there's some value. If you actually store these two things side by side, you might as well not be doing it. So definitely bear that in mind.
Yeah, and we saw this in a couple of breaches where they had encrypted the database and then they stored the key that they encrypted the database with on the server, on the database server, right? And so when the attacker got access to it, they dumped the database, grabbed the key, and decrypted everything, right? I think, Paul touched on something that I think is important. When we talk about how to make these decisions, the absolute #1 most important thing that you need to do is come up with what your threat model is, right? And this is a good question as developers when a security team or a compliance person or someone shows up and tells you to do a thing. The #1 question you want to ask them is, what threat model are we talking about? What am I trying to protect against, right? Is it root level access on my server? Because there's not a lot you can do to protect against stuff like that. Is it SQL injection? Is it somebody has access to a database backup? Is it an internal person that works for a company that we want to protect against, right? So understanding what problem you're trying to solve is the same with all development, right? But in security, it's especially important. Understanding what problem you're trying to solve will drive you to the right solution, because there are certain solutions that will get very, very difficult for you to do anything about, right? Root level access on your server that has the encrypted data or has the key, it's very hard to protect against something like that, right? And so spending an enormous amount of effort spinning around trying to do that is where you get these weird systems where keys are encrypted with keys, and it all boils down to security through obscurity. Like once you know how it works, right, then you can get the stuff that you need out of it.
I think the one thing you're kind of glossing over is like key rotation, and like once you are compromised, what do you do about it? And if you have a really simple solution on a bazillion servers and you don't have a way to like rotate it, like I feel like you're saying, oh, keep it simple, but honestly, it has to be complex to be able to be resilient and to deal with threat.
So it depends. I mean, I think if you use the right constructs, then none of this is simple, right? When you get underneath the covers, even Fernet is very complex and makes very specific decisions about what threat it's protecting against and all that. I mean, you're absolutely right in that there are things that you have to do to make your system, somewhat future-proof so that you can do some of the things like key rotation. But those things don't have to be enormously complex.
I feel like the secret storage thing is like this unanswered question in the industry.
Yeah.
It absolutely is.
No, you're absolutely right. And that's one of the reasons why we spent a little bit of time on it. It's not very interesting to say, oh yeah, store it in a config file, store it in the environment. You all knew that coming in here, right? But we wanted to show it specifically because the questions I get all the time was, there has to be some other way to do this that's better. To be honest, there really isn't right now, right? Not without getting really crazy. And even the really crazy solutions don't offer a huge amount of security over the real basic ones. But the ugly fact of the matter is that the vast majority of applications are built with the stupidest possible option, right? And that's, those are the guys that are getting popped and losing stuff. That being said, you see people who know what they're doing, right? Like the Slack guys know what they're doing. They still got popped, right? Like you can't keep them out. So you do the best job that you can, and then you focus on what happens when they do get in, right? That you have some level of protection and that you're able to rotate keys and respond to that. Did you want to say something?
Well, basically, basically everything that Jarret just said in that, yeah, key rotation is really hard. However, the Rui Goldberg systems that you were describing don't add security typically, or in many cases make it worse. And they still don't fix the fact that you need to do key rotation at some point. So I think you're they're orthogonal. Does that make sense? Like you can.
Yeah, I guess it's not really, a problem with storage so much as being able to respond to a compromise.
Yes.
Yeah, and I think the hard part to that is knowing when you're building a Rube Goldberg thing and knowing when you're building the thing that you actually need, right? Yes, hire a cryptographer. That's not a really good answer. All right. So, do you want to take a break?
So we got 27 minutes left. So
okay.
We can go through.
So we'll power through the end here. So we've only got a half an hour left. So we'll talk a little bit about asymmetric encryption. Asymmetric encryption in this case is also known as public key cryptography. So you'll hear that a lot as how it's referred to, right? And so in this particular case, for symmetric encryption, right, we have the same key for encryption and decryption. Right? Asymmetric encryption, we have different keys for encryption and decryption. This all makes very sense, right? So it's asymmetric because it's two different keys. And that gives you that public-private key nomenclature that you see, right? And so the nice thing about this is that it allows you to share 1/2 of the keying material, right? So I keep my private key to myself, obviously, right? But my public key can be known by anyone, right? And that allows me to, I can encrypt something with my private key that can be decrypted by public keys. We can sign things. We're talking about all kinds of fun stuff that happens with that construct, right? When these were first starting to come out, there was this assumption that symmetric encryption would go away, right? Because asymmetric is better, right? In every way, it's better. Except it turns out that it's actually not, right? So there's some restrictions to asymmetric that make it not useful in a lot of cases. One, there's restrictions to the size that can be used with certain constructs, the size of data that can be used with certain constructs. And the separate piece of it is that it's sadly pretty slow, right? So when you start talking about TLS, for example, or HTTPS, right, when you're using all that type of stuff, the asymmetric piece of that is actually a handshake. It does a little bit of asymmetric encryption, but the only thing that it passes between the two of them is a symmetric key. And once you've agreed on that symmetric key, then they actually just use symmetric encryption for the entire actual connection that they have there, and that's really for performance, right? There are probably other reasons why you don't want to do that too, but I'm not going to get too deep into that, right? But generally, where you're going to see asymmetric encryption, where you're going to want to start using that, is when you have to start passing data between parties or between two systems. Now, sometimes those can be two systems that you own. A lot of times those are two systems that you don't necessarily own one half of it, right? So you need to share data with somebody outside of your control, right? And so now you want to have a keying material structure where you can give them a key that you're not worried about them having. And the other thing is you'll use it for is around trust and verification, so signing, right? And we'll talk about that hopefully if we have enough time.
Yeah, so once we start talking about asymmetric encryption, things get a little trickier. So PKI, the public key infrastructure, is, to put it mildly, a complex topic. And it's perhaps the most poorly implemented thing in the history of the internet. There are a lot of problems, and many of them are not currently all that surmountable. Some of them are endemic to the way it's actually designed, and some of them are problems with the fact that various libraries have defined what they consider to be the standard, and one of them has become dominant enough that what it considers to be the standard pretty much is the standard, even if it happens to be wrong. So those things can be problematic. The other one that I guess I would, before we move on this, I would say is asymmetric cryptography is substantially more complex than symmetric cryptography. Key generation is substantially harder. It is no longer, it's like to get an AES key, to get almost any symmetric encryption key, you just ask os.urandom for the number of bytes you need. To get an RSA key, it is actually a sequence of, it's a special set of primes that have certain characteristics so that you can do operations in a very specific way. And to generate those, you need to run it through, like basically a random number generator sits there and produces things until it gets the primes that it needs at the bit sizes you've specified. And then you do that many, many times potentially. Depending on how large your key is. The larger your key, the more the less probability that you're going to get it right initially. So generating those keys is hard. Using those keys is even harder. The implementations typically have lots and lots of ways that they can leak information via what's called side channels. So you have to have all sorts of extra techniques to actually protect your keys when they're being used. In the case of RSA, there's a thing called RSA blinding, where you introduce an additional blinding factor such that you can't easily obtain the private, the D, which is the private exponent, without some extra work. However, even that isn't necessarily enough. Actually, there was recently a very interesting attack against, was that libgcrypt? It was against the GPG, right? Where it was a power analysis attack, which essentially meant they were using the implementation of GPG to see how much power it consumed while it was doing certain operations to recover the bits of the key, but they did it using sound. They actually did it like they used I think it was a Dell laptop.
So it works for it was the ThinkPad. Well, there was a ThinkPad.
Oh, it was the ThinkPad too. Yeah.
So yeah, basically, your computer has a bunch of capacitors in it because. In a room exactly like this one, doing a bunch of encryptions. I've been sending email. I've been doing GPG. Like, for all I know, some of you have some really good microphones. Actually, you have a really good microphone. I should be worried. But no, seriously, like the supersonic hum created by capacitors. Like at this point, it sounds like the X-Files, but actually a real attack.
Yep, and they were able to reliably obtain the key. So then GPG did an implementation change to make it so that was much harder. But the point here is that like asymmetric encryption, these types of side channels are not unheard of by any means on the symmetric side, but they are far more common and far more problematic on the asymmetric side.
Measuring, getting the key from a microphone. Whew.
Yep. So there's actually some very interesting attacks that have recently come out using cache faulting. Essentially, if you have two VMs side by side on the same hypervisor, you can intentionally try and fill up the level 2 cache while something else is attempting to compute like an AES operation. And if they don't have hardware AES, AES tends to expand what's are called its S boxes. It creates these. It creates basically a two-dimensional table for lookups, and those things load into L2 cache because, of course, the processor wants to do it fast. And if you sit there with another virtual machine attacking that, causing page faults, you can then read. You can then, based on the timing of reloading that cache, you can figure out what those tables look like, and therefore recover the AES key.
Yeah. Suffice it to say, it's
Yeah. So in general, like most of there's a very interesting and active area of research around building cryptographic constructs that are not vulnerable to these concepts. Most notably championed by, as I mentioned earlier, Daniel J. Bernstein, DJB. He's the author of QMail and TinyDNS and some of those things. He has some very, very interesting ideas. He writes some very, very cool code. However, those things are right now not standardized. You're starting to see a lot more of that, especially in the wake of certain Snowden NSA revelations, especially around the way NIST's own standards were somewhat subverted in certain cases. So you're starting to see an increased interest in his stuff, especially around his symmetric cipher, a symmetric stream cipher, Cha-Cha-20, and his MAC, which is that's message authentication code, which he calls Poly 1305. So in the next versions of TLS, you're actually going to see cipher suites that support Cha-Cha-20 plus Poly 1305, in addition to things like AES plus Galois counter mode.
mainly from Google at the moment.
And I apologize for all the...
Yeah, so suffice it to say, when you're looking at asymmetric encryption, it's much easier to rely on existing systems, even though those existing systems have problems. So TLS or SSL is the obvious one that you see most often, right? You know, if you use TLS 1.2, then you're in reasonably good shape, at least as far as we know at the moment.
For now.
The amount of work going into breaking these types of systems and stuff like that is increasing, and that's why you're seeing a lot more stuff coming out about these particular constructs, because they're very, very difficult to get right, way more than we thought they were originally when everybody started building them. So, all right, so we have one last section on signing and verification. How much time do we have left? Like,
We have 18 minutes.
18 minutes. So we can kind of go through this, and I'm happy to walk through the signing and verification piece. If you guys have questions that we'd rather talk about first, happy to do that, and we can kind of skip this. So up to you guys. Anybody have any questions that they wanted to ask and be about any of the stuff we talked about today, or anything else that you've run into at work? Any of those things are fine. Could all just be playing Sudoku for all I know.
Slides posted, by the way?
They will be. We will put them up for anybody who wants them. Yeah. Yeah.
So you mentioned that for like just injecting the environment variables into your code, there were a couple better ways to do it, but you were like, it's too long, so we're not going to put it. Do you think you just give like these are the 3 ways?
Like, where would you go to find?
Yeah.
Like, where should we read?
Do you want?
That's a good question. Now you want to take
We're going to duck this one. So there are a couple of different ways to do it. So if you look at Rails, for example, they have a pretty decent plugin that allows you to specify a .env file, .env, that gets deployed along with your app, stays outside of source control, but it's deployed as part of the app deployment process. And when the application server loads your particular application, it actually reads that .env file, dumps that stuff in. Heroku, for example, allows you to specify the .env files as you're going forward. That's probably about state of the art today. One of the things that people are starting to work on, it's something that we've been playing with, is the idea of using Barbican, which is a system we talked about, and having an agent that actually reaches out to a third-party system to grab your secrets and then exposes them in the environment variables to a particular process under certain constraints, right? So you could specify that, oh, my process needs to have this hash, right? So we're going to make sure that no one's running a fake version of LS or something like that. Or it's only exposed for X amount of time after a reboot or whatever it happens to be. That stuff's still very researchy, and I don't think anybody's really using it right now. In addition to that, I mean,
You guys using it? Is Rackspace using Barbican?
we're using Barbican, but we haven't done the work to build the agent and that kind of stuff yet. So Barbican is mostly being used by other OpenStack projects who need to store keys. So the load balancer project, or if you're looking at Nova and it wants to encrypt disks and stuff like that, then they're using Barbican on the back end to store it. That's all still very new code. I don't think most of that's even made it into OpenStack yet, so there's still some work there before people can do it. But something that's being actively worked on. I think one of the things that I like to hit on for the key management piece is, at the end of the day, most of us are moving towards a configuration management world. Right, so your applications are being managed by Chef or Puppet or one of these systems. Even when you're looking at moving to Docker containers and various other things where you're talking about immutable infrastructure, a lot of times that immutable infrastructure is actually created by a configuration management system, Ansible or something along those lines. Even a Docker file is technically a configuration management system. It's just not a very advanced one. So at the end of the day, when you are building a system using those tools, you are explicitly trusting those tools. Your infrastructure lives only at the behest of your Chef server. If someone owns your Chef server, that's the ballgame, right? They own your infrastructure. There's nothing you can do to protect against that, right? So you are explicitly trusting those. So then putting your secrets in a configuration management system is not making you any less secure. Right now, you're not going to put them in source control or do any of that kind of stuff because that's different threat models, right? But at the end of the day, you already explicitly trust your Chef server. You have to. Right? So Chef encrypted data bags, Salt, any of these types of things, these are perfectly reasonable ways to drop a configuration file on a disk that has secrets in it, right? That's fine. So I wouldn't worry too much about those things, right? As we said before, there's not really any other option that offers a significant amount more security without really damaging very deeply the way that you write software. So hopefully that answers your question a little bit. Yeah, this is a disappointing answer, but.
Said that trusting at that point you're trusting the configuration management tool is incredibly important because Salts screwed up their crypto 3 times in a row. And one of the things okay, well, okay, we've talked about, you don't want to harp on them because, people make mistakes all the time, but in particular, configuration management software should be held to a much higher standard than everything else because it pretty much definitionally has access to all of your machines, and not just access, root access. So, yeah.
Yeah, Chef at its heart is a rootkit for all intents and purposes, right? It sits on your box and it can do anything to it. And that's actually what you want it to do. There's nothing wrong with that model. That's the model that they've chosen, and that's the best job that they can do. I think as we start looking down the road at what could fix some of these problems, right? Containers get very interesting where you're starting to kind of source, you're by definition moving all of the configuration data out of a particular container. Now, obviously containers can be built 18 bajillion different ways, but there's some interesting work there around things like etcd and various other things that are starting to understand, oh, well, maybe we'll have a way to expose secrets that's different. And because right now, the problem right now is you generally have to expose your secret kind of very widely across your infrastructure. And if you could expose your secret in a very narrow case where it's only available to this server only when it needs it, and I can track every single time that somebody touches it, and I can alert when someone touches it outside of the policy that I put in place, then you actually start to get into some stuff. Right? Now, you'll never necessarily be able to protect people from getting your key, but again, if you can detect that and then have the software ability to be able to remediate that very quickly, then you're in very good shape. So.
And for those who are curious about how the Salt, one of the Salt vulnerabilities actually worked, this goes back to RSA and other asymmetric things are hard. RSA is based on a problem called the integer factorization problem. It's a problem believed to be hard, not proven to be hard, but believed to be hard. And the best known solution to it right now is what's called the general number field sieve. So RSA does certain things, but one of those things is it exponentiates. So it takes a public exponent and exponentiates against certain things. So you can set that public exponent to a variety of values. Best practice these days is to set it to 65,537, but 3 is actually fine except for certain. There are certain low-grade attacks that can happen if you make mistakes with small exponents, so everyone just says, make it a large exponent, it's fine. Salt set their exponent to equals 1. So what is 1 to any power?
Anything to the power 1.
Yeah, anything to the power 1. My mistake, sorry. Yeah. It's always the same value. So it meant that their encryption was not doing anything. And
the encryption was literally just returning exactly the same number. It was doing absolutely nothing, so that was highly unfortunate. But yeah.
All right, I thought there was another hand back here somewhere. Yes?
Just real quick, I have something where I do have a need to sort of send asymmetric messages over a channel I can't control, so I can't sort of use TLS, sort of bouncing around an email, not quite. So you're looking at Keyser, so it has a handy asymmetric encryption that's supposed to be idiot-proof, like for NetBase for symmetric. We're using
So Keyzar is a fine solution. Yeah, the Keyzar protocol was originally developed by Google. They've got both the symmetric and the asymmetric stuff, and it's a completely fine solution that has a nice upgrade path. Be a little careful between, there's Keyzar 1 and Keyzar 2. And Keyzar 1 has effectively been abandoned by Google, and Keyzar 2 is the new hotness that they care about. So you have to be a little careful. If you can use Keyzar 2, you should probably go that route because the support will be longer term. Certainly there are other projects inside the Python world, my own included, that have been looking at whether or not we should go ahead and implement Keyzar support such that people who need to migrate from it or want to consume it can continue to use it.
Yeah. Yeah, Keyzar. Yeah, Keyzar's generally fine. I don't think anybody's had any problems with it.
I mean, the only other, quote, asymmetric, like high-level things that exist are like PKCS7 and CMS. And if you can avoid those, please do. CMS and PKCS7, so CMS is the successor to PKCS7, so it pretty much encompasses the entire complexity of PKCS7 plus adds more. It also contains all of X509, which is the PKI certificate stuff. It gets very hairy very quickly, and if you can avoid it, that's great. So yeah, I would definitely recommend. In fact, I can't think of a better option right now than using Keyzar.
All right, any other questions? Anything else you guys want to talk about? We'll just finish the last slide. We just won't do the example here. Cool. All right, we'll talk a little about signing and verification. Go ahead.
Which we already kind of did. But.
Yeah, we've talked a little bit about this in the past. So signing and verification is about data that you want to authenticate, right? You want to be able to understand who sent it to you. You want to be able to understand that what was sent to you by that person has not been modified by someone else in the middle, right? But you don't care that anyone else knows the contents of the message, right? So we're not talking about confidentiality here. We're talking about authentication and identity in this case. So basically the signing verification problem kind of has a couple of different pieces that you have to have available, right? So you need to be able to generate a key, right? You need to be able to sign something, and then you need to be able to verify it. And then the side piece of that is you need to be able to actually store these things together. Because in a lot of cases, you've got some data that you're signing. Let's say it's a PDF or something like that you want to sign. You're not actually modifying the PDF, but the PDF has no way to include the digital signature, which you actually do want, right? Although PDF's maybe a bad example because it actually does have that because Adobe built it. But say it's an image file or something like that, right? There's no built-in support in JPEG for being able to store a digital signature to make sure that that JPEG hadn't been modified. So a lot of times if you're building a system in which you want to exchange a message like this, you'll want a construct that actually includes the digital signature. You can always send them separately. It's no big deal, but a lot of times it's easier if you can do that. I don't know if you want to go through most of this, but
I can do with this. So a common example I'm sure you guys have seen quite a bit is OAuth. So OAuth uses HMAC signatures, and it uses those to confirm that the person who's attempting to make a connection has a secret token, and the other side agrees that the same secret token was used to construct this signature and that the data that was transmitted has not been tampered with. This is fairly common usage. You can use it for almost any API. There's kind of two primary approaches. There's more than two, but two I can think of right now, so clearly only two. One of the approaches for communicating with an API is every time you communicate with that API, you're going to send your token along with it, and the server will say, yes, I agree, that token is a token that I recognize because I checked it via quality, whatever. Maybe it did a password hash against it, like you were passing your password or something. The other way to do it is that you do something like an HMAC signature across the data you're sending. Both sides know that they have the same secret, so that all the other side has to do is verify the HMAC signature. That means that if for whatever reason you have maybe you have a really bad API that's not using TLS to secure its endpoints, that's unfortunately very common, although you definitely should always secure your endpoints with TLS. At that point, this is data going across in the clear. Well, hypothetically, it could be tampered with. You could read the API key. Well, if you're doing an HMAC signature across it, it can't be tampered. It cannot be tampered with, and there is no API key. You can't see it. All you see is an HMAC signature that the other end verifies.
Yeah, so there's an example that's in the code base that you guys can dig into if you want to. I don't think we'll have time to go through it today, but it's there if you want it. So a good example for this type of stuff you'll see, so Amazon uses the latter, where you're actually doing some HMAC stuff when you send messages to the Amazon API, whereas OpenStack, for example, kind of does the former, right? You pass your key or your API key every single time you make a request to the API. One open question for you, I get this a couple of times every once in a while, is if I'm using TLS, do I have to also sign stuff, right? Generally, the answer is no. TLS provides both confidentiality and integrity. Pretty much, yes. So the only place where I've ever seen that it is required is if you're dealing with some FIPS level stuff. So if you're doing some things for the feds and it needs to be FIPS level qualified, then there is some double encryption stuff that goes on. But there's nothing preventing you from doing it, of course. But I don't think you don't have to, because TLS provides both of those guarantees.
There is, however, an interesting implementation detail when you're building larger scale applications, and that is, where do you terminate your TLS? So if you choose to terminate your TLS at an F5 at the very front, and then it transits plain text back through your systems, which is a pretty common situation. One, you shouldn't do that. You should re-encrypt again, and you should have your own internal TLS certificate hierarchy if you need to, or just buy public certificates, which is much simpler to do that. But if you don't, if for whatever reason you have some requirement that you terminate TLS and then everything's plain text behind it, HMAC actually provides additional guarantees. It says that, this is again talking about whether or not you're developing a threat model. If that threat model is that the attacker has passive or even potentially active network access, but not necessarily box level access. So they have not compromised a VM, but they can introspect traffic on that network. If you have an HMAC on it, then you're okay. They can see what's happening. That's bad, of course, depending upon what you're doing, but they can't tamper with it, and they can't, and any tampering that they would do would cause a failure. If you don't HMAC it, then now they can actually completely tamper with it. Maybe you, like I as a user, sent a request to download a specific file, my 1099B tax form. Now that you have an attacker inside that network that intercepts that request and changes it so that it sends someone else's 1099B. That's obviously a very big problem, especially because that's personally identifying information. It's possible that you actually even stored that data encrypted, but you've now actually tricked the entire system, bypassed all authentication, and obtained the file that you shouldn't have gotten.
Yeah, and I think like when you see stuff like this, we kind of like to think, oh, well, hey, that doesn't happen very often, right? Like once I pull it into my application infrastructure, that application infrastructure is relatively safe. So you can trust that, oh, hey, I'm terminating TLS at the top, and underneath it, I own all that stuff, right? And all you need to do is go look at some of the slides that came out in the Snowden revelations around how they had tapped Google. Google had this idea that their back-end networks that they had paid for were secure, and so they weren't running TLS on top of them. And the NSA took advantage of that and tapped there. Right. In fact, if you've seen that slide where it says encryption added in here and it's got a little smiley face or whatever on the side of it, it was the NSA basically laughing about the fact that Google made an assumption that wasn't true. Right. So even the best in the business do this stuff. So it may make sense, depending on the data that you're talking about, how sensitive it is and how much it matters to your system, that you HMAC or encrypt and use TLS. In general, for most systems, deploying TLS, if you can get everything deployed with TLS across your entire organization, throw a party, because nobody does that, right? So if you can get that stuff done, right, that is amazing. Anything above that is gravy. All right, any more questions or anything else you guys want to talk about? All right, so Paul and I will be here for the rest of the conference. Paul's staying for the sprints. LVH over here in the corner is an actual cryptographer as opposed to us. He's a crypto engineer. I'm just a dabbler at this point. So we'll be around. If you have any questions, you want to talk to us, please feel free to come. I want to thank you guys for coming for this. It's obviously fun for us to do, but at the same time, it's always great for us to be able to see people who are interested in doing this stuff the right way and trying to increase our knowledge about that. So thank you guys for coming and spending time with us. Hopefully we didn't bore you too much. Rackspace paid for the USB keys. You're welcome to keep them. If you don't want them, you can toss them in the box. Entirely up to you. I think that's it. All right, great. Thanks, guys.